Hey guys, welcome back. Tonight, we're going to drift somewhere extraordinary. Somewhere so extreme, so impossibly vast and violent and strange that even describing it feels a little absurd. We're going to explore the most extreme objects ever discovered in space. Not planets, not stars, not the familiar landmarks you've seen in textbooks. We're talking about things so dense they warp reality. Objects so bright they outshine entire galaxies. Places so cold that time itself seems to pause. And stretches of emptiness so vast they make our entire solar system look like a grain of sand forgotten on a cosmic beach. These are the extremes, the edges of what's possible, the universe showing off. And here's the strange part. All of it is real. All of it exists right now, somewhere out there, doing impossible things while you sit here in your quiet room, breathing air, existing on a small blue rock that suddenly feels very, very gentle by comparison. You know that feeling when you're standing at the edge of the ocean at night? The way the darkness stretches out ahead of you, endless and unknowable. And for just a moment, you feel both incredibly small and strangely peaceful. That's what tonight is going to feel like. Except instead of water, it's space-time. And instead of the horizon, it's the edge of everything that exists. By the end of tonight, you'll understand just how wild the cosmos can get. And hopefully, you'll drift off to sleep feeling strangely comforted by your own smallness. Because here's a secret the universe teaches anyone who pays attention. Being small isn't a tragedy, it's a relief. It means you don't have to hold everything together. The cosmos does that on its own. Before we go any further, if you enjoy this kind of calm, curious exploration, a like or subscribe genuinely helps the channel grow. But only if you actually enjoy this. No pressure. It's a small thing for you, but it makes a real difference for me. And if you have a favorite extreme object, something that keeps you up at night wondering, leave it in the comments. I read them. I appreciate them. They help me know what to explore next. Now let's begin. Dim the lights if you haven't already. Turn on a fan if that helps. The white noise tends to smooth out the edges of the world. Adjust your pillow. Pull the blanket up. Settle in. And as you do, let yourself wonder for a moment. What does it feel like to stand near something so dense that a teaspoon of it weighs 1 billion tons? How do you measure distance when the nearest neighbor is 100,000 years away at our fastest speed? What happens when a star dies so violently it outshines everything in the observable universe? For just a few seconds, what would you think if you found out the universe has places colder than the emptiness between galaxies? Would you feel terror? Or something quieter? Something like awe? Have you ever considered that right now, somewhere out there, a star is being born? And somewhere else, one is dying? That the universe is constantly reshuffling itself, building and destroying, with a patience that makes human history look like a single heartbeat? Let's find out together. Slowly, your room begins to fade. The walls dissolve into darkness. The hum of your world grows quieter. The refrigerator, the distant traffic, the neighbor's television bleeding through the walls, all of it softens, recedes, and in its place, you feel something vast opening around you, an endless, patient blackness, punctuated by pinpricks of ancient light. You're no longer in your room. You're drifting through the cosmos now, surrounded by silence, surrounded by distance, surrounded by objects so extreme they barely seem real, and yet they are. Let's begin with the first one. Segment 1. Neutron stars, the impossible density. Imagine taking the entire mass of our sun, 1 million Earths worth of material, and crushing it into a sphere the size of a small city. Not a country, not a state, a city, about 12 miles across. That's a neutron star. A teaspoon of its material would weigh roughly 6 billion tons on Earth. You couldn't lift it. You couldn't move it. You couldn't do anything except stare at it and quietly accept that physics has lost all sense of proportion. Neutron stars are born in violence. When a massive star, something 8 to 20 times the mass of our Sun, exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses inward in a fraction of a second. Protons and electrons are crushed together so forcefully that they merge into neutrons. And what remains is a ball of matter so dense that our normal vocabulary starts to fail. Let's put this in perspective. If you took Mount Everest, the entire mountain, rock and ice and all, and compressed it down to the size of a sugar cube, you still wouldn't come close to the density of a neutron star. The atoms themselves have been squeezed out of existence. There are no empty spaces, no room between particles, just neutrons, packed shoulder to shoulder in an eternal, unimaginable embrace. The gravity on the surface of a neutron star is about 200 billion times stronger than the gravity on Earth. If you somehow found yourself standing on one, which you couldn't because you'd be flattened into a layer of atoms thinner than a sheet of paper, but if you could, and you dropped a marshmallow from a height of 1 meter, it would hit the surface with the force of a nuclear bomb. A marshmallow, 1 meter. The universe, it turns out, has a very dark sense of humor, and yet, for all their violence, neutron stars are strangely beautiful. They glow, not brightly, not like our Sun, but with a faint, residual heat left over from their cataclysmic birth. Over millions of years, they cool, they fade, they become darker and quieter, but they never disappear. They simply persist, dense, patient, waiting for the end of time. Some neutron stars spin, and not slowly. Some rotate hundreds of times per second, faster than a kitchen blender, faster than anything that size has any right to spin. Their magnetic fields are trillions of times stronger than Earth's. They can emit beams of radiation so intense that we can detect them from thousands of light years away. But here's the part that tends to keep physicists awake at night. We don't fully understand what's happening inside a neutron star. The outer layers we can model. The crust we can estimate. But the core? The very center of that impossibly dense sphere, it might contain forms of matter that don't exist anywhere else in the universe. Quark soup, strange matter, things we've only theorized but never observed. It's a bit like knowing there's a room in your house that you've never been able to open. You can knock on the door, you can press your ear against it, but you can't get inside, and you're not entirely sure what would happen if you did. So tonight, as you lie there, imagine drifting slowly past one of these objects. You don't get close. No one gets close. But you can feel it somehow. The weight of it. The way it bends the space around it, like a bowling ball sitting on a trampoline. Light curves toward it. Time slows near its surface, and at its heart, something impossible is happening, something that might take us centuries more to understand. That's a neutron star, a teaspoon of eternity. Let's drift onward. Segment 2, magnetars. When magnetic fields become weapons. Now, let's take that neutron star we just visited, that impossibly dense ball of crushed matter, and give it a magnetic field so powerful it defies comprehension. What you get is a magnetar. And if neutron stars are strange, magnetars are terrifying. A magnetar's magnetic field is roughly a quadrillion times stronger than Earth's. That's a 1 with 15 zeros after it. At that strength, magnetism stops being a force and starts being a physical presence. If you were within 1,000 miles of a magnetar, the magnetic field would begin to distort the electron clouds around your atoms. Your molecular structure would stretch. The chemistry that holds you together would fail. You wouldn't explode. You would simply stop being a coherent object. And that's at 1,000 miles. Get closer, and things become even more unsettling. The magnetic field becomes so intense that it affects the vacuum of space itself. It polarizes the emptiness. Light passing through that region bends and distorts. The very fabric of reality starts behaving differently than it does anywhere else in the universe. But here's the truly remarkable part. Magnetars are unstable. Their crusts, the thin, dense shells of crystallized matter that surround their cores, are under constant stress. And sometimes, that crust cracks. When it does, the magnetar releases what's called a starquake, a sudden, violent readjustment of its surface that sends shock waves rippling outward. In December 2004, a magnetar located about 50,000 light-years away experienced one of these starquakes. The burst of energy it released was so powerful that it briefly affected Earth's upper atmosphere. Not the light from it, the actual radiation, traveling across 50,000 light-years of empty space, still had enough energy to ionize particles in our ionosphere. For a fraction of a second, a crack on the surface of a dead star halfway across the galaxy reached out and touched our planet. Think about that for a moment. A starquake on an object 12 miles wide, 50,000 light-years away, and we felt it. If that magnetar had been closer, say, within 10 light-years, the effects would have been catastrophic. The radiation could have stripped away our ozone layer, exposed the surface to lethal cosmic rays, and fundamentally altered the conditions for life on Earth, all from a single crack on a single object in a galaxy full of billions of stars. And yet, we don't often think about magnetars. They're not on the news. They don't trend on social media. They just exist out there, spinning quietly in the dark, occasionally cracking their own surfaces and sending death rays across the cosmos. It's a little like finding out that somewhere in your neighborhood, there's a sleeping dragon that occasionally snores fire. You hope it stays asleep. You hope it stays far away. But you can't stop thinking about it. What makes magnetars so magnetic? The truth is, we're not entirely sure. The leading theory is that it has to do with the way they're born, the specific conditions of the supernova that created them, the initial spin rate, the dynamics of the collapsing core. Some neutron stars become magnetars, most don't. The universe once again is rolling dice we can't see. Tonight, as you drift further from this strange object, you might notice something curious. Even at a great distance, you can feel the pull. Not gravity, magnetism, an invisible hand tugging at the iron in your blood, at the charged particles in your cells. It's faint, it's harmless, but it's there, a reminder that even empty space is full of forces, tensions, invisible threads connecting everything to everything else. Let's keep moving. Segment 3, pulsars, the universe's lighthouses. Some neutron stars spin, and as they spin, they emit beams of radiation from their magnetic poles. If those beams happen to sweep past Earth, like the rotating light of a lighthouse, we see a pulse, a flash, a rhythmic signal emerging from the darkness. These are pulsars, and when they were first discovered in 1967, they were so strange, so regular, so unlike anything natural we'd ever seen, that the astronomers who found them briefly wondered if they were signals from an alien civilization. They even jokingly labeled the first one LGM-1 for little green men. They weren't aliens, of course. They were something stranger, rapidly spinning neutron stars, some completing hundreds of rotations per second, their beams sweeping across the cosmos with the precision of atomic clocks. In fact, some pulsars keep time more accurately than any clock humans have ever built. They lose perhaps 1 second every few million years. The universe, it seems, is better at engineering than we are. Let's picture what's actually happening here. You have a sphere about 12 miles across, roughly the size of Manhattan, spinning so fast that a point on its equator is moving at a significant fraction of the speed of light. It's emitting beams of intense radiation from 2 points on its surface, like a demented cosmic disco ball. And every time one of those beams sweeps past our little corner of space, our instruments register a pulse. Some pulsars pulse once every few seconds. Others pulse hundreds of times per second, so fast that if you converted the signal to sound, it would be a high-pitched whine, a note in the cosmic symphony. There's something almost musical about pulsars. They have rhythm. They have regularity. In a universe characterized by chaos and randomness, they're remarkably dependable. But here's the thing. Pulsars don't last forever. They slowly lose energy. Their rotation gradually slows. Over millions of years, they spin down, their beams weaken, and eventually they fade into ordinary neutron stars, dense, dark, and silent. Every pulsar you've ever heard of is dying in slow motion, winding down like a cosmic clock that no one will ever rewind. And yet, new pulsars are born all the time. Every supernova that produces a neutron star has a chance of producing a pulsar. The universe is constantly replenishing its supply of cosmic lighthouses, even as the old ones fade. Scientists use pulsars for all sorts of things. They've been used to confirm Einstein's theories of general relativity by measuring how their signals change as they pass through curved space-time. They've been used to search for gravitational waves by looking for tiny variations in their timing, and they've been proposed as navigational beacons for future spacecraft, a kind of cosmic GPS, using the universe's most reliable clocks to determine position. There's something comforting about pulsars. In a universe full of unpredictable violence, gamma-ray bursts, supernovae, magnetar flares, pulsars just keep spinning. They don't care about our problems. They don't care about our schedules. They simply rotate, pulse, and persist, like the ticking of a grandfather clock in an empty house. Tonight, imagine you can hear one, a faint, steady beat coming from somewhere far away. Not threatening, not demanding, just present. A heartbeat in the darkness, a reminder that even in the most extreme places, there can be rhythm. There can be regularity. There can be something almost like music. Let's drift a little deeper. Segment 4. Black holes, where physics goes to surrender. A black hole is not a thing. It's an absence, a place where gravity has become so overwhelming that nothing, not light, not time, not even space itself, can escape. Cross the event horizon, and you don't come back, not because of walls, not because of barriers, but because all directions lead inward. The very concept of away no longer exists. At the center of a black hole, or at least as far as our mathematics can take us, there's something called a singularity, a point of infinite density, a place where our equations produce infinities and break down entirely. We don't know what actually happens there. Our physics, quite literally, cannot describe it. It's as if the universe took our carefully constructed theories, looked at them, and said, "Not here. Here, the rules are different. Black holes come in different sizes. Stellar black holes, born from the collapse of massive stars, typically range from a few to a few dozen times the mass of our Sun. Intermediate black holes, which we're still trying to understand, might contain hundreds or thousands of solar masses. And supermassive black holes, the monsters at the centers of galaxies, contain millions or even billions of times the mass of our Sun. But here's what's remarkable. A black hole isn't complicated. In fact, it's one of the simplest objects in the universe. It can be fully described by just 3 properties: mass, spin, and electric charge. That's it. All the complexity, all the information that went into creating it, the star that collapsed, the matter that fell in, is gone, erased, hidden behind the event horizon forever. Physicists call this the no-hair theorem, and it's one of the strangest ideas in modern physics. What happens if you fall into a black hole? It depends on the black hole's size. For a stellar black hole, the tidal forces, the difference in gravitational pull between your head and your feet, would tear you apart long before you reach the event horizon. This process has a wonderfully technical name: spaghettification. You would be stretched into a long, thin strand of atoms, a thread of what used to be you, spiraling inward toward oblivion. For a supermassive black hole, things are different. The event horizon is so large that the tidal forces at the boundary are actually quite gentle. You could cross it without even noticing, at least not immediately, but you'd never be able to tell anyone outside. And from that moment on, your future would contain only one destination: the singularity. No matter which way you turned, no matter how fast you traveled, all paths would lead inward. Time itself would conspire against you. From the outside, watching someone fall into a black hole would be equally strange. As they approached the event horizon, time would appear to slow down for them. They'd move more and more slowly, their light stretching into redder and redder wavelengths, until eventually they'd seem to freeze at the boundary. A fading image, growing dimmer and dimmer, but never quite disappearing. Time dilation and redshift working together to create an eternal goodbye. And yet, for all their terrifying properties, black holes are essential. They shape galaxies. They influence the movement of stars across thousands of light years. They may play a role in how the universe itself evolved. Without black holes, the cosmos might look very different, and life perhaps might never have emerged at all. There's something almost poetic about that. The most destructive objects in the universe might also be among the most necessary. The universe builds with one hand and destroys with the other, and sometimes those hands are the same. Let's keep drifting. Segment 5. Sagittarius O. The monster at the center of our galaxy. At the heart of the Milky Way, roughly 26,000 light-years from where you're lying right now, there's a supermassive black hole. We call it Sagittarius A. Pronounced Sagittarius A star, it contains the mass of about 4 million suns, compressed into a region smaller than our solar system. We can't see it directly. Black holes, by definition, don't emit light, but we can see its effects. Stars near the galactic center orbit it at tremendous speeds, some completing full orbits in just a few decades. By tracking these stars, astronomers have mapped out the gravitational influence of Sagittarius A with remarkable precision. They know exactly where it is, how massive it is, and how it shapes the space around it. In 2022, scientists released the first image of Sagittarius A1. Not a photograph exactly. Black holes don't photograph well, but a radio image showing the glowing ring of superheated gas that surrounds the event horizon. The shadow at the center, the dark circle where no light escapes, is the black hole itself. After decades of indirect evidence, we finally saw the thing we'd always known was there. And it's patient. Sagittarius A isn't currently feeding, at least not heavily. It's relatively quiet compared to the active supermassive black holes at the centers of other galaxies. But it wasn't always this way. Millions of years ago, it likely went through periods of intense activity, consuming gas and dust, producing jets of radiation that would have been visible across the galaxy. And it will almost certainly become active again in the future. There's something humbling about living in a galaxy with a monster at its heart. Every star you see in the night sky is, in some sense, orbiting that central point. The entire galaxy, hundreds of billions of stars, trillions of planets, countless moons and asteroids and comets, all of it is held together, in part, by the gravity of Sagittarius AC. It's the anchor, the quiet center around which everything else turns. And yet, from your perspective, it's invisible, hidden behind 26,000 light years of stars and dust and gas. You'll never see it with your naked eyes. You'll never feel its pull directly. It's simply there, like a deep note in a symphony too low for human ears, present, influential, and utterly beyond ordinary perception. Tonight, as you settle into sleep, consider this. Every atom in your body has been circling that black hole for billions of years. You've made countless loops around the galactic center, drifting through space, orbiting a monster you've never seen, and you'll continue orbiting it for the rest of your life, and long after you're gone. Let's drift a little further. Segment 6, TON 618, the largest black hole we've ever found. If Sagittarius A is impressive, TON 618 is incomprehensible. Located about 10 billion light-years away, so far that the light we see from it left when the universe was less than half its current age. TON 618 is one of the most massive black holes ever discovered. It contains approximately 66 billion times the mass of our Sun. That number is so large that it stops meaning anything. Let me try to put it in perspective. Our entire solar system, the Sun, all 8 planets, all the moons, all the asteroids, everything, would fit comfortably inside the event horizon of TON 618. Not just fit, but be swallowed without making a noticeable difference. The event horizon is larger than the orbit of Neptune. It's a sphere of no return, roughly the size of our entire cosmic neighborhood. Think about that for a moment. Neptune orbits the Sun at an average distance of about 4.5 billion kilometers. That's the edge of our solar system in practical terms, the boundary beyond which our Sun's influence begins to fade. TON 618's event horizon spans that entire distance and more. If you placed TON 618 where our Sun sits, you would already be inside it. Earth would be inside it. Mars, Jupiter, Saturn, all of them, gone, consumed by a boundary from which nothing, not even light, can escape. And the mass, 66 billion suns. Our Sun is already almost impossible to comprehend. A ball of plasma so large that you could fit 1.3 million Earths inside it, burning hydrogen into helium at a rate of 600 million tons per second. Now multiply that by 66 billion. Every second, TON 618 contains the mass equivalent of 66 billion stars like ours, compressed into a singularity smaller than an atom. We don't have mental frameworks for this. Our brains didn't evolve to understand objects this large. We can say the numbers, write them down, manipulate them mathematically, but truly grasping what they mean, that's beyond us, and perhaps that's okay. Perhaps the universe is allowed to contain things we cannot fully hold in our minds. TON 618 is growing. It's a quasar, an active galactic nucleus surrounded by a disk of superheated matter spiraling inward. That disk is so hot, so bright, that it outshines the entire galaxy in which it resides. We can see it from 10 billion light years away because it's one of the brightest objects in the observable universe. All that brightness comes from destruction, matter being torn apart and converted to energy as it falls toward oblivion. The accretion disk around TON 618 is a maelstrom of violence that we can barely imagine. Gas and dust spiral inward, accelerating to significant fractions of the speed of light. Friction between particles heats the disk to millions of degrees. At these temperatures, matter glows with such intensity that it drowns out the light of hundreds of billions of stars. The energy released is equivalent to converting matter directly into pure radiation, the most efficient energy production process in the known universe. And jets. TON 618 likely produces jets of particles and radiation shooting outward from its poles at nearly the speed of light, extending for thousands or even millions of light years into space. These jets are so powerful that they can heat surrounding gas, prevent new stars from forming, and reshape entire galaxies. A black hole, in essence, reaching out across cosmic distances to influence the structure of the universe itself. How does something like TON 618 form? The honest answer is, we're not entirely sure. The universe is only about 13.8 billion years old. For a black hole to grow this large, it would need to consume matter continuously for most of cosmic history, or it would need to start with a significant head start. Some astronomers propose that the first black holes, formed in the early universe, were already more massive than stellar black holes today. These seed black holes might have collapsed directly from massive clouds of primordial gas, bypassing the stellar phase entirely. Others suggest that black holes can grow through mergers, swallowing each other and combining their masses. When galaxies collide, and they do frequently over cosmic time, their central black holes eventually spiral toward each other and merge. Each merger creates a larger black hole, which can then consume more matter, grow larger, and merge again. Over billions of years, this process could produce the monsters we observe today. There's also the Eddington limit to consider, the theoretical maximum rate at which a black hole can consume matter. Beyond this limit, the radiation pressure from the accretion disk would blow incoming material away, preventing further growth. But TON 618 seems to have exceeded what simple calculations would predict. Perhaps it fed more efficiently than we understand. Perhaps the early universe provided conditions we haven't accounted for. Perhaps there are aspects of black hole physics we haven't yet discovered. The mystery remains, and in some ways, that's part of what makes TON 618 so fascinating. It's not just an object, it's a question, a challenge to our understanding, a reminder that the universe is under no obligation to be easily explained. Either way, TON 618 represents something remarkable: the universe's capacity to build things so large that they exceed our ability to imagine them. We can say 66 billion solar masses. We can write the number. But can we actually understand what it means? Probably not. Our brains evolved to comprehend the scale of rivers and mountains, not the scale of supermassive black holes. Consider what it would be like to approach TON 618. From a distance, you might not even notice it. Black holes don't shine on their own. They're defined by the absence of light. But as you drew closer, you'd see the accretion disk, a swirling band of brilliance encircling what appears to be a perfectly dark sphere. The sphere would grow larger as you approached, eventually filling your entire field of view. And at some point, You wouldn't know exactly when you'd cross the event horizon. You'd still be falling, still experiencing time and space, but your fate would already be sealed. No force in the universe could pull you back. What's inside? We don't know. General relativity predicts a singularity, a point of infinite density where the known laws of physics break down. But infinite density is probably just our mathematics confessing its limitations. Something is there, at the center, something real. We just don't have the physics to describe it yet. And that's okay. Not understanding something fully doesn't diminish it. If anything, it makes it more wonderful. There are objects in the universe that we will never fully grasp, no matter how long we study them. TON 618 is one of them. It exists at the edge of our comprehension, a monument to the scale of reality that extends far beyond human experience. When you look up at the night sky, you can't see TON 618. It's too far away, too faint without instruments, too lost among the countless other points of light. But it's there. It's been there for billions of years, and it will remain there for billions more, growing slowly, shining brightly, utterly indifferent to whether anyone notices. Let's keep moving. Segment 7. Quasars, brighter than a trillion suns. A quasar is what happens when a supermassive black hole feeds. As matter spirals inward, gas, dust, sometimes entire stars, it forms an accretion disk, a flattened structure of material orbiting the black hole at tremendous speeds. Friction and gravitational forces heat this disk to millions of degrees. And at those temperatures, it glows. Not just glows, blazes. A single quasar can outshine an entire galaxy of stars. Hundreds of billions of stars combined, producing less light than one feeding black hole. It's as if someone turned the brightness up so high that everything else faded into the background. To understand how remarkable this is, consider the Milky Way. Our galaxy contains somewhere between 200 and 400 billion stars. Each of those stars is a nuclear furnace, converting hydrogen into helium and releasing energy in the process. The combined output of all those stars is staggering, and yet a single quasar can outshine it all. Not by a small margin, but by factors of hundreds or even thousands. One object at the center of a galaxy, producing more light than everything else combined. The physics behind this is almost elegant in its simplicity. When matter falls into a black hole, it doesn't fall straight in. Conservation of angular momentum causes it to spiral, forming a disk. Within this disk, particles collide with each other, generating friction. That friction converts orbital energy into heat, and at the temperatures reached in the inner regions of an accretion disk, tens of millions of degrees, matter radiates energy with extraordinary efficiency. In fact, accretion onto a black hole is the most efficient known mechanism for converting matter into energy. Nuclear fusion, which powers stars, converts about 0.7% of matter's mass into energy. Accretion onto a black hole can convert up to 40%. Nearly half of everything that falls in is radiated away as light, X-rays, and other forms of radiation before it crosses the event horizon. The black hole is destroying matter and in the process, illuminating the universe. Quasars were first discovered in the 1960s, and they confused astronomers for years. They looked like stars, point sources of light, but their spectra were strange, shifted in ways that didn't make sense for nearby objects. Some astronomers thought they might be a new type of star within our own galaxy. Others wondered if they represented unknown physics. It took Martin Schmidt in 1963 to realize what was happening. The strange spectral lines weren't unknown. They were hydrogen lines, shifted dramatically toward the red end of the spectrum. This redshift indicated that the objects were moving away from us at tremendous speeds, which meant they were very far away. And if they were very far away, they had to be incredibly bright to appear as visible as they did. The name quasar comes from quasi-stellar radio source, because some of the first ones discovered were strong radio emitters. Today, we know that not all quasars are radio loud, and we've dropped the radio source part. But the name stuck. These quasi-stellar objects, points of light that looked like stars but weren't, had revealed something profound about the universe. At the time, the idea that anything could be that bright seemed almost impossible. How could a single object outshine a galaxy? The answer, we now understand, lies in the supermassive black holes at galactic centers. When these black holes have access to abundant fuel, they become active. They consume matter voraciously, producing the brilliant displays we call quasars. Today we know that quasars are just one phase in the life of a galaxy. When a supermassive black hole has plenty of material to consume, it becomes active. It produces jets of energy that can extend for thousands of light years. It lights up the surrounding space, and then, eventually, the fuel runs out. The quasar fades. The black hole becomes dormant, still massive, still dangerous, but no longer shining. The jets produced by quasars deserve special attention. These are beams of particles and radiation shooting outward from the black hole's poles at nearly the speed of light. They can extend for millions of light years, far beyond the galaxy that hosts the quasar, reaching into intergalactic space. When these jets collide with surrounding gas, they heat it, preventing new stars from forming. In this way, a quasar at the center of a galaxy can regulate star formation throughout the entire galaxy, even in regions millions of light years from the black hole itself. It's a strange form of cosmic influence. The black hole consumes matter near the center of the galaxy, and in doing so, it affects processes at the galaxy's edge. Cause and effect spanning distances we can barely comprehend. Most galaxies, including our own, probably went through quasar phases in their youth. Billions of years ago, before the Milky Way settled into its current spiral shape, Sagittarius A might have been a quasar, brilliant, violent, and visible from across the universe. Now it's quiet, resting, waiting for the next meal. There's evidence for this in the structures around our galactic center. Astronomers have detected what appear to be ancient jet remnants, bubbles of hot gas extending above and below the galactic plane, relics of a more active past. The Fermi bubbles, as they're called, are structures spanning 50,000 light years, and they may be the fading echoes of a time when our galaxy's heart burned brightly. Today, Sagittarius A is relatively quiet. It consumes only small amounts of matter, and its luminosity is a tiny fraction of what it could be. But give it fuel, a cloud of gas drifting too close, or a star torn apart by tidal forces, and it could flare up again. Not to quasar levels, perhaps, but brighter than it is now. The potential for violence is always there, lying dormant. There's something almost biological about this cycle. Galaxies feeding, growing, going dormant, then feeding again. Black holes at their centers acting like hearts, pulsing with energy during active periods, quiet during rest. The universe is full of processes that mirror the rhythms of life, even though none of them are alive in any sense we'd recognize. Consider the life cycle. A galaxy forms from collapsing gas in the early universe. At its center, a black hole grows. When fuel is abundant, the black hole feeds, becoming a quasar that outshines everything around it. The quasar's jets blow gas out of the galaxy, eventually cutting off the fuel supply. The quasar fades, the galaxy settles, stars form and die, and eventually, perhaps through a merger with another galaxy, new gas flows toward the center, and the cycle begins again. Birth, growth, rest, rebirth. The patterns of life, written in the language of gravity and light. Tonight, imagine you could see a quasar without any instruments, just your eyes, looking up at the sky. You'd see a point of light, bright, steady, unremarkable at first glance. But that point contains more energy than your mind can hold. It's a beacon from the distant past, a signal from a universe that was younger, wilder, and more violent than the one we inhabit now. The light from a distant quasar has been traveling for billions of years. When it left its source, Earth didn't exist. Our sun hadn't formed. The atoms that would one day become you were scattered across the cosmos, not yet assembled into planets or people. And now, after all that time, a few of those ancient photons are entering telescopes, telling us about a universe we never could have visited. There's something humbling about that. We're observers, catching glimpses of a past that's inconceivably old, studying objects that are inconceivably distant. The quasar doesn't know we exist. It doesn't care. It's just doing what physics demands, consuming matter, radiating energy, shining across the void. And it's still out there, still shining, waiting for its light to reach some distant future observer. Billions of years from now, the universe is patient. It has all the time in the world. Segment 8, Gamma-ray bursts, the universe's most violent moments. A gamma-ray burst is the most energetic event in the known universe. In just a few seconds, it releases more energy than our sun will produce in its entire 10 billion year lifetime. If one happened within a few thousand light years of Earth, and if it were pointed at us, it could sterilize the entire planet. These events come in two types. Short gamma-ray bursts, lasting less than 2 seconds, are thought to occur when two neutron stars collide, or when a neutron star collides with a black hole. Long gamma-ray bursts, lasting anywhere from a few seconds to several minutes, are associated with the deaths of extremely massive stars. Supernovae so violent that they produce focused jets of gamma radiation shooting outward at nearly the speed of light. To understand the violence of a gamma-ray burst, consider the energy involved. A typical long gamma-ray burst releases about 10^44 joules of energy in its initial flash. That's a number with 44 zeros after it. For comparison, our sun releases about 3.8 x 1026 joules per second. Even at that rate, it would take the sun more than 10 billion years to release as much energy as a gamma-ray burst does in seconds. And all that energy is concentrated. Gamma-ray bursts don't radiate uniformly in all directions. They're focused into jets, cones of radiation shooting outward from the collapsing core. If you happen to be in the path of one of those jets, you receive the full force of the explosion. If you're off to the side, you might not see it at all. The universe's most powerful explosions are also, in a sense, selective. They choose their victims by geometry. The discovery of gamma-ray bursts came about almost by accident. In the late 1960s, the United States launched a series of satellites called Vela, designed to detect nuclear weapons tests in space. The satellites worked perfectly, but they found something unexpected. They detected brief, intense flashes of gamma radiation coming from space, clearly not from any nuclear weapons. The bursts were kept classified for years before being revealed to the scientific community in 1973. At first, no one knew what to make of them. Gamma rays are the highest energy form of electromagnetic radiation, and producing them in such quantities requires extreme conditions. Some astronomers thought the bursts must be relatively nearby, within our own galaxy perhaps. Others suspected they were coming from much farther away, which would make them far more energetic. The debate raged for decades. It wasn't until 1997 that astronomers were able to identify the optical afterglow of a gamma-ray burst and determine its distance. The burst had occurred in a galaxy billions of light years away. That settled the question. Gamma-ray bursts were cosmological events, not local ones. And that meant they were even more powerful than anyone had imagined. When a gamma-ray burst occurs, space itself seems to scream. The burst is followed by an afterglow, radiation across the electromagnetic spectrum, from X-rays to radio waves, that can persist for weeks or even months. By studying these afterglows, astronomers can learn about the environment in which the burst occurred, the distance to the source, and the physics of the explosion itself. The afterglows have taught us a great deal. We've learned that long gamma-ray bursts tend to occur in small, irregular galaxies with low metallicity, galaxies where star formation is still vigorous and massive stars are common. We've learned that the jets move at 99.99% the speed of light or faster, producing relativistic effects that amplify the observed brightness. We've learned that the bursts are often followed by supernovae, confirming the connection between gamma-ray bursts and the deaths of massive stars. In 2017, astronomers detected gravitational waves from the merger of two neutron stars, and just 1.7 seconds later, a gamma-ray burst was observed from the same location. This was the first direct confirmation that neutron star mergers produce short gamma-ray bursts. It was also a triumph of multi-messenger astronomy, combining gravitational wave detection with traditional electromagnetic observations to study a single event. The physics of what happens inside a gamma-ray burst is still not fully understood. When a massive star's core collapses, or when two neutron stars merge, the resulting object is a compact remnant, either a neutron star or a black hole, surrounded by a disk of hot, dense material. Magnetic fields thread through this disk, and somehow, through processes we're still working to understand, energy is channeled into narrow jets that punch through the outer layers of the star and shoot outward into space. The jets are where the gamma rays come from. Internal shocks within the jet, where faster moving material catches up with slower moving material, produce the initial burst of gamma radiation. External shocks, where the jet collides with surrounding material, produce the longer-lasting afterglow. It's a complex interplay of fluid dynamics, magnetic fields, and relativistic physics, occurring in conditions so extreme that we can only study them indirectly through the radiation they produce. But here's the reassuring part. Space is vast, and gamma-ray bursts are rare. The odds of one occurring close enough to Earth and pointed directly at us are astronomically small. Most bursts happen in distant galaxies, billions of light years away. We detect them, we study them, and we marvel at their violence from a very safe distance. Some scientists have speculated that a gamma-ray burst might have caused mass extinctions in Earth's past. The Ordovician-Silurian extinction, about 450 million years ago, wiped out roughly 85% of marine species. Some researchers have suggested that a gamma-ray burst might have been responsible, damaging the ozone layer and allowing harmful ultraviolet radiation to reach the surface. But this remains speculative. There's no direct evidence for such an event, and other explanations, like volcanic activity or climate change, are also plausible. Even if a gamma-ray burst contributed to past extinctions, we shouldn't lose sleep over the possibility of future ones. The odds are genuinely tiny. The nearest known candidate for a gamma-ray burst, A star called WR104, which might someday collapse into a supernova powerful enough to produce one, is about 8,000 light-years away, and its jets don't appear to be pointed at us. Even if they were, 8,000 light-years is probably far enough that the effects would be minimal. Still, there's something unsettling about knowing they exist. Somewhere out there, right now, a gamma-ray burst is occurring. A star is collapsing, or two neutron stars are merging, and a beam of pure destruction is lancing through space at the speed of light. It will never reach us, but it's happening. The universe is constantly producing these moments of extreme violence, even as we lie here in our quiet rooms, drifting towards sleep. It's a little like knowing that somewhere on Earth, a volcano is erupting, or a lightning bolt is striking, or a wave is crashing against a cliff. Violence is always happening somewhere. The scale just varies. There's a strange comfort in that, if you think about it. The universe is dynamic. It's constantly changing, constantly producing events of unimaginable power. And yet, here we are, on a quiet planet, in a peaceful corner of the galaxy, untouched by the violence that rages elsewhere. We're protected by distance, by probability, by the sheer vastness of space. The gamma-ray bursts will continue. Stars will collapse. Neutron stars will merge, and we'll watch from afar, gathering data, building understanding, marveling at the power of events we'll never experience directly. Let's move on to something quieter. Segment 9, Supernova Remnants, the Ashes of Giants. When a massive star dies, it doesn't go quietly. It explodes outward at a significant fraction of the speed of light, scattering elements forged in its core across light-years of space. What remains is a supernova remnant, an expanding shell of glowing gas, enriched with iron and oxygen and carbon and gold. The violence of a supernova is difficult to overstate. In the moment of explosion, the outer layers of the star are accelerated to speeds of 10,000 kilometers per second or more. Shock waves ripple outward, compressing and heating the interstellar medium. The energy released is equivalent to what our sun will produce over its entire 10 billion-year lifetime, released in a matter of seconds. And yet, from this violence, something beautiful emerges. The expanding shell of gas glows with colors that depend on its composition. Oxygen produces blue-green hues. Hydrogen glows red. Sulfur adds yellows and oranges. The result is a celestial tapestry, a work of cosmic art painted by the death of a star. The Crab Nebula is perhaps the most famous supernova remnant. It was created by an explosion that occurred in 1054 AD, an event so bright that it was visible during the day and recorded by astronomers in China, Japan, and the Middle East. Nearly 1,000 years later, the remnant is still expanding, still glowing, still visible to anyone with a decent telescope. Historical records of the 1054 supernova are fascinating. Chinese astronomers called it a guest star and noted that it was visible even in daylight for 23 days. It remained visible to the naked eye at night for nearly 2 years. Imagine looking up at the sky and seeing a new star, brighter than anything else, impossible to ignore, knowing that it wasn't there before and not knowing what it meant. Today, we understand what they saw: the death of a massive star, located about 6,500 light-years away, ending in a cataclysmic explosion that briefly outshone everything else in the sky. The light from that explosion took 6,500 years to reach Earth, which means the star actually died around 7,500 years ago in absolute terms. But for us, for our ancestors who recorded the event, it happened in 1054. Inside the Crab Nebula, at its center, is a pulsar, the spinning neutron star left behind by the explosion. It rotates about 30 times per second, sending beams of radiation sweeping across space like a cosmic lighthouse. The nebula itself is powered, in part, by energy from this pulsar. It's a cosmic engine, still running after a millennium, still producing light from its own ongoing destruction. The Crab pulsar is losing energy constantly. Its rotation is slowing down, imperceptibly but measurably, as it radiates energy into the nebula. This energy keeps the nebula glowing even after 1,000 years. Without the pulsar, the Crab Nebula would have faded long ago. It's a partnership between the dead star and its remains, the one feeding energy to the other, keeping the light alive. But the Crab Nebula is just one example. There are hundreds of known supernova remnants in our galaxy, each with its own history, its own structure, its own story to tell. Cassiopeia A is another famous remnant, located about 11,000 light-years away. Unlike the Crab Nebula, its explosion wasn't recorded by historical astronomers, possibly because it was obscured by interstellar dust, or possibly because it occurred during a period when astronomical observation was less systematic. But we can see it now, and it's spectacular. A shell of glowing filaments, rich in silicon and sulfur and oxygen, expanding outward at 5,000 kilometers per second. Cassiopeia A is also home to a neutron star, though not a pulsar. The neutron star at its center is the youngest known in our galaxy, only about 340 years old. We can study it to learn about the immediate aftermath of a supernova, the cooling of a newborn neutron star, the physics of matter in its most extreme states. Then there's the Veil Nebula, a remnant that's much older, about 10,000 to 20,000 years old. It's expanded so much that it now spans a region of sky 6 times the width of the full moon, but it's also faint, requiring long exposures to photograph properly. The Veil Nebula is a supernova remnant in its twilight, slowly merging with the surrounding interstellar medium, eventually to become indistinguishable from it. All supernova remnants share this fate. They expand, they cool, they fade. After perhaps 100,000 years, they're no longer recognizable as distinct structures. The elements they scattered have mixed with the surrounding gas, enriching it with the heavy elements that will one day become part of new stars and planets. Supernova remnants are important for a reason beyond their beauty. They seed the universe with heavy elements. Everything heavier than iron is created in supernova. Gold, silver, platinum, uranium. These elements are scattered into space, where they eventually become part of new stars, new planets, new life. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now. All of it was forged in the hearts of massive stars and scattered by their deaths. The process is called nucleosynthesis, and it's one of the most important in all of cosmic history. In the cores of massive stars, lighter elements are fused into heavier ones, hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. Each fusion reaction releases energy, which supports the star against gravitational collapse. But when the star reaches iron, the process stops. Fusing iron doesn't release energy, it absorbs it, and without energy to support it, the core collapses. In that collapse, and in the explosion that follows, elements heavier than iron are created. The extreme temperatures and pressures allow neutron capture, a process where atomic nuclei absorb neutrons and transform into heavier elements. Gold, silver, platinum, uranium, all the heavy elements that make our technology possible, that make our jewelry beautiful, that make our nuclear reactors work, were created in the deaths of stars. You are, quite literally, made of supernova remnants. The universe exploded, and some of those explosions became you. There's something almost sacred about that. Not religious, necessarily, but profound. Every atom in your body has a history that stretches back billions of years to events of unimaginable violence occurring in stars you'll never see. You carry the ashes of giants inside you. Consider the gold in any jewelry you might own. Those atoms were created in a supernova, or perhaps in the merger of two neutron stars, another event capable of forging heavy elements. They were scattered into space, drifted for millions of years, became part of a collapsing cloud of gas, were incorporated into our forming solar system, found their way into Earth's crust, were mined and refined by human beings, and now sit on your finger or around your neck. That's the journey of every heavy atom, from stellar death to human life. It's a connection that spans the cosmos. We are not separate from the stars. We are made of them. Every element in our bodies, every atom in our world, has a cosmic origin. We are the universe experiencing itself, the matter of dead stars arranged into patterns complex enough to wonder where it came from. Tonight, as you drift toward sleep, consider that you are not separate from the cosmos. You are part of it. You're made of the same material. You're participating in the same slow, vast processes of creation and destruction that have been occurring since the beginning of time. And when you're gone, your atoms will return to the cycle. They'll become part of new stars, new planets, new beings. The universe recycles. Nothing is ever truly lost. The supernova that created the iron in your blood didn't know it was contributing to a being who would one day exist. And you don't know what beings your atoms might one day become. But the cycle continues, indifferent to our awareness, beautiful in its persistence. Segment 10. The Bode's Void, a hole in the universe. Somewhere in the direction of the constellation Bode's, there's a region of space roughly 330 million light-years across that contains almost nothing. Not emptiness between stars, that's normal. This is emptiness between galaxies. Where you'd expect to find thousands of galaxies, there are perhaps 60. It's called the Bode's Void, and it's one of the largest known voids in the observable universe. If our Milky Way were at its center, we wouldn't have known that other galaxies existed until the 1960s. The sky would have been almost completely dark, just our own stars, and beyond them, nothing. Think about what that would have meant for human history. For most of our existence, we believed we were at the center of everything. The Earth was the cosmic hub, with the sun and planets and stars revolving around us. It took Copernicus and Galileo and Kepler to dislodge us from that position, to show us that Earth orbits the sun, not the other way around. And it took Edwin Hubble, in the 1920s, to show us that the Milky Way isn't the whole universe, that those spiral nebulae we'd been observing were actually other galaxies, millions of light years away. But if we'd been inside the Bode's Void, Hubble's discovery would have been delayed by decades. There would have been no spiral nebulae to observe, or at least very few. The Andromeda Galaxy, our nearest large neighbor, would have been too far away to see. We might have concluded that the Milky Way was alone in the cosmos, an island of stars in an infinite sea of darkness. It's a reminder of how much our understanding depends on our location. We happen to live in a relatively crowded part of the universe, surrounded by galaxies and clusters and structures that hint at the larger cosmos. Someone living in the Bode's Void would have a very different view and might have reached very different conclusions about the nature of reality. how does something like this form? The universe isn't uniform. In the early moments after the Big Bang, there were tiny fluctuations in density, some regions slightly denser, others slightly emptier. Over billions of years, gravity amplified these differences. Dense regions pulled in more matter, becoming galaxies and clusters. Empty regions grew emptier, becoming voids. The structure of the universe, on large scales, resembles a cosmic web. Galaxies and clusters are concentrated along filaments, long, thread-like structures that span hundreds of millions of light years. Between the filaments are voids, regions of relative emptiness where few galaxies exist. The Buddha's void is simply an unusually large example of this pattern, but it is unusually large. Most voids are smaller, tens of millions of light years across, not hundreds. Some astronomers have suggested that the Buddha's void might be the result of several smaller voids merging together over time. As the universe expands and structures evolve, voids can grow and combine. Perhaps the Buddha's void started as several separate empty regions that have since merged into one enormous empty space. Others have proposed more exotic explanations, though none have gained widespread acceptance. Some have speculated about unusual physics in the early universe, or about the effects of primordial gravitational waves. But the honest answer is that we don't fully understand why this particular void is so vast. The universe is under no obligation to make itself easily comprehensible. What we do know is that it exists, and standing inside it, if you could stand inside it, would be one of the loneliest experiences imaginable. No nearby galaxies, no cosmic neighbors, just your own stars, and beyond them, an abyss of darkness extending for hundreds of millions of light years in every direction. Imagine the night sky from a planet inside the Buddha's void. Your own galaxy would still be there, the Milky Way equivalent, with its billions of stars spanning the sky in a glowing band. But beyond that, almost nothing. A few faint smudges, perhaps, barely visible even with telescopes. No Andromeda, no Magellanic Clouds, no clusters or superclusters to hint at the larger structure of the cosmos. Your astronomers might never discover that other galaxies exist, or they might discover it very late with very powerful telescopes and be stunned to find that the universe is far more crowded than they'd ever imagined, just not where they were. The sense of isolation would be profound. Not just personal isolation, but cosmic isolation. A galaxy alone in a void, surrounded by emptiness on a scale that defies comprehension. And yet, even the Buddha's void isn't truly empty. Those 60 or so galaxies are still there, scattered through the darkness. They're not clustered together. They're spread throughout the void, isolated from each other, each one an island in a vast empty sea. Some of them might have their own planets, their own life, their own civilizations, wondering why the universe seems so empty. It makes you appreciate how crowded our part of the universe actually is. We have the Andromeda Galaxy just 2.5 million light years away. We have dozens of smaller galaxies in our local group. We have the Virgo cluster, the Great Attractor, structures upon structures extending outward in every direction. We're not isolated. We're part of a cosmic community. The nearest large galaxy cluster to us is the Virgo cluster, about 54 million light years away. That's close enough that we can study its galaxies in detail, observe their shapes and motions, understand how clusters work. Beyond Virgo, there are more clusters, more superclusters, more structure, all the way out to the edge of the observable universe. We're embedded in a network, connected in a sense to everything around us by gravity, by light, by the cosmic web that links galaxies and clusters across billions of light years. That's a privilege. That's a gift of location, Not everyone in the universe is so lucky, but somewhere out there, that community ends. And beyond it, there's just space. The Buddha's void is a reminder that the universe has room for emptiness as well as fullness, that not every corner of the cosmos is teeming with structure. That loneliness on a cosmic scale is possible. There's something meditative about that, about contemplating a void so large that your entire cosmic neighborhood could fit inside it and still be lost, about imagining the silence of those empty regions where light travels for millions of years without encountering anything at all. The universe contains multitudes. It contains clusters and galaxies and stars and planets, but it also contains voids, vast, quiet regions where almost nothing happens. Both are part of the cosmic story. Both deserve our attention and our wonder. Segment 11, the great attractor, the thing pulling everything. Something is pulling our galaxy and hundreds of thousands of other galaxies toward a point in space we can barely observe. It's hidden behind the densest part of the Milky Way, blocked from our view by dust and stars. We call it the great attractor. It has the gravitational pull of millions of billions of suns, and we're all moving toward it, slowly, steadily, whether we notice or not. The discovery of the great attractor came about through careful observation of galactic motions. In an expanding universe, galaxies should be moving away from each other in all directions, carried by the expansion of space itself. But when astronomers measured the actual motions of galaxies in our cosmic neighborhood, they found something unexpected. There was a systematic drift. Galaxies weren't just expanding away from each other, they were also moving toward a particular direction in space, a region in the constellations Centaurus and Hydra. The Great Attractor was discovered in the 1970s, when astronomers noticed that galaxies in our region of space weren't moving the way they should. The expansion of the universe should be carrying everything outward, but something was pulling us in a particular direction, toward the constellations Centaurus and Hydra, at about 600 kilometers per second. 600 kilometers per second. That's over 2 million kilometers per hour, and we're all moving at that speed, right now, without feeling anything. The Earth carries us along, orbiting the Sun. The Sun carries us along, orbiting the galactic center. And the entire Milky Way carries us along, falling toward the Great Attractor. We're nested inside motions within motions within motions, all happening simultaneously. For decades, we couldn't see what was there. The zone of avoidance, the region of sky obscured by the Milky Way's disk, blocked our view. The Milky Way's disk is filled with dust and stars that absorb and scatter light, making it nearly impossible to observe what lies beyond in certain directions. The Great Attractor happens to sit almost exactly in this zone, hidden behind the densest part of our galaxy. It's a cosmic irony. One of the most important gravitational influences on our region of space is hidden from view by the galaxy we inhabit. We can infer its presence from the motions of galaxies, but we can't see it directly, at least, not in visible light. But with infrared and radio telescopes, we've gradually pieced together what lies beyond. Infrared light and radio waves can pass through the dust that blocks visible light. Using these wavelengths, astronomers have mapped the region behind the zone of avoidance and discovered what's causing the gravitational pull. The Great Attractor isn't a single object. It's a vast concentration of mass, including the Norma cluster, one of the most massive galaxy clusters known, all working together to create a gravitational well that's tugging at everything around it. The Norma cluster alone contains thousands of galaxies, each with billions of stars. And it's just one part of a larger structure, a supercluster that spans hundreds of millions of light years. Think of it like a drain in a bathtub. Water flows toward the drain, drawn by gravity. The Great Attractor is like a drain in the cosmic ocean, a concentration of mass that creates a valley in the fabric of space-time, drawing everything toward it. We're floating on that current, drifting toward a destination we'll never reach. And beyond the Great Attractor, there's something even larger, the Shapley Supercluster. Some astronomers now think that the Shapley Supercluster is the true source of the gravitational pull, with the Great Attractor serving as an intermediate concentration along the way. We're being pulled toward a hierarchy of structures, each larger than the last. The Shapley Supercluster is one of the most massive structures in the observable universe. It contains tens of thousands of galaxies, concentrated in a region about 650 million light-years away. Its gravitational influence extends for hundreds of millions of light-years, affecting the motions of galaxies throughout our cosmic neighborhood. We're falling toward it, or rather, we're being pulled toward it. But the expansion of the universe is working against this pull. Space itself is stretching, carrying galaxies apart even as gravity tries to draw them together. On the largest scales, expansion wins. We'll never actually reach the Shapley Supercluster. We'll never fall into the Great Attractor. The universe is expanding too fast. It's a little like finding out there's a drain at the far end of your bathtub and you've been drifting toward it your whole life, except the bathtub is billions of light years across and the drain is a supercluster of galaxies you'll never reach. And the water is expanding, stretching the distance between you and the drain, even as you drift toward it. Don't worry though, the expansion of the universe is still dominant on cosmic scales. We'll never actually fall into the Great Attractor. We're just moving in its direction, drawn by gravity, while space itself stretches around us. The two forces, gravitational attraction and cosmic expansion, are playing a slow-motion tug of war, and expansion is winning. In the far future, this will become even more pronounced. As the universe continues to expand, distant galaxies will recede from us faster and faster. Eventually, they'll cross an horizon beyond which their light can never reach us. The observable universe will shrink, and we'll be left with just our local neighborhood, the galaxies gravitationally bound to us, falling toward each other, even as everything else falls away. But that future is billions of years distant. For now, we can still observe the Great Attractor, still measure its pull, still wonder at the structures that shape the universe on its largest scales. There's something humbling about learning that we're not stationary. We think of ourselves as fixed, as stable, as located in one place, but we're moving constantly, rotating with the Earth, orbiting the Sun, circling the galaxy, falling toward the Great Attractor. Every moment, we're somewhere new. Every second, we're millions of kilometers away from where we were. The universe is dynamic. Nothing is still. And the Great Attractor is one of the forces that shapes our motion, a gravitational giant hidden from view, pulling us toward a destination we'll never reach. Segment 12. Hypervelocity stars, runaways from the galactic core. Some stars are traveling so fast that they will eventually escape the Milky Way entirely. These hypervelocity stars were likely flung outward by close encounters with the supermassive black hole at the galactic center, gravitational slingshots that sent them hurtling through space at millions of miles per hour. Imagine the scenario. A binary star system drifts too close to Sagittarius A. The black hole's gravity captures one star and flings the other outward at tremendous speed. In an instant, A star that was peacefully orbiting the galaxy is now on an escape trajectory, heading out into intergalactic space, never to return. The physics of this process is both violent and elegant. Binary star systems, two stars orbiting each other, are common in the galaxy. When such a system passes too close to Sagittarius A, the gravitational forces become extreme. The star closer to the black hole experiences a stronger pull than the one farther away. This difference in force can tear the binary apart. One star is captured by the black hole, possibly falling in or becoming part of the swarm of stars orbiting the galactic center. The other star is ejected. The energy that was holding the binary together is transferred to the ejected star, accelerating it to enormous speeds. It's a cosmic slingshot, using the black hole's gravity to convert orbital energy into velocity. The ejected star doesn't just move fast, it moves fast enough to escape the entire galaxy. The Milky Way's gravity is substantial, holding hundreds of billions of stars in orbit. But a hypervelocity star is moving so fast that even all that gravity can't hold it. It's on a one-way trip to intergalactic space. We've discovered dozens of hypervelocity stars. Some are traveling at speeds exceeding 1,000,000 miles per hour. At those velocities, they'll leave the Milky Way within a few million years. A blink of an eye, cosmically speaking. The first hypervelocity star was discovered in 2005. It was a blue star, about 240,000 light-years from the galactic center, moving outward at about 1.6 million miles per hour. Since then, astronomers have found many more, using surveys that measure stellar motions with high precision. Each one is a clue to the violent dynamics at the heart of our galaxy. Not all hypervelocity stars come from the galactic center. Some might have been ejected by supernovae. When a binary companion explodes, the remaining star can be flung outward at high speed. Others might have been ejected by close encounters with other stars or stellar remnants. But the fastest of them, the ones truly on escape trajectories, almost certainly interacted with Sagittarius A. Only a supermassive black hole has the gravitational power to create such extreme velocities. And then what? What happens to a star that leaves its galaxy? They'll spend the rest of their existence traveling alone, between galaxies, in the vast emptiness where almost nothing else exists. No nearby stars, no planets to warm. Just an endless journey through the intergalactic void, glowing faintly until their fuel runs out, then cooling slowly into darkness. The intergalactic medium is the loneliest place imaginable. There are no stars within light years. There's nothing to see, nothing to orbit, nothing to interact with. Just space, cold, dark, empty space, extending in every direction for millions of light years. A hypervelocity star traveling through this void would continue to shine, of course. It still has fusion occurring in its core, still produces light and heat. But that light would radiate outward into emptiness, never reaching anything. The star would be alone in a way that few objects ever are. Eventually, the star would exhaust its fuel. Depending on its mass, it might become a white dwarf, or a neutron star, or even a black hole. But whatever it becomes, it would remain alone, drifting through intergalactic space for eternity, a remnant of a galaxy it once called home. It's a lonely fate. And yet, there's something almost heroic about it. These stars have escaped the gravity that holds the rest of us in place. They've broken free. They're the universe's runaways, the cosmic rebels who refuse to stay where they were put. Of course, they didn't choose this. They were flung. The universe, once again, makes the decisions. But we can still admire them from afar, these wanderers between worlds. these stars without homes. Some of them might even carry planets. If a hypervelocity star had a planetary system before its ejection, and many stars do, some of those planets might have survived the violent event and remained bound to the star. They would be carried along into intergalactic space, worlds without a galaxy, orbiting a star without neighbors. Could life exist on such a planet? It seems unlikely. The journey through intergalactic space would take millions or billions of years, and the lack of cosmic stimulation might make evolution difficult. But life is tenacious. Who knows what might be possible? There's a science fiction quality to hypervelocity stars. The idea of a world hurtling through the darkness between galaxies, its inhabitants looking up at a sky devoid of stars except their own sun. It sounds like fantasy, but it might be happening right now, somewhere in the universe. We can't follow them. We can't send probes to investigate. We can only observe them from afar, tracking their motions, calculating their trajectories, imagining their journeys. The hypervelocity stars are beyond our reach, literally escaping the galaxy, moving into realms we may never explore. But knowing they exist is enough. Knowing that the universe has room for such extremes, for stars moving at millions of miles per hour, for journeys spanning intergalactic distances, for escapes from galactic gravity, is enough. The cosmos is more dynamic, more violent, more strange than we often imagine, and hypervelocity stars are one more reminder of that strangeness. Segment 13: Rogue Planets, Worlds Without Stars. Not all planets orbit stars. Some were ejected from their solar systems early in their formation, flung into the darkness between stars, wandering alone. They have no sunrise, no seasons, no warmth except what they generate internally. And there may be billions of them drifting through our galaxy right now, cold, silent, invisible, except when they pass briefly in front of something else. The idea of a planet without a star seems almost contradictory. We think of planets as companions to stars, worlds warmed by stellar light, orbiting in predictable paths, defined by their relationship to a central sun. But the universe is messier than our definitions. Planets can exist without stars, and many do. Rogue planets are difficult to detect. They don't emit light. They don't orbit anything we can track. They're cold, dark objects drifting through the void, revealing themselves only through indirect means. The primary method for finding them is gravitational microlensing, a phenomenon where a planet's gravity bends the light of a more distant star, briefly magnifying it. When astronomers see this magnification in their data, they know something massive passed between them and the star. Sometimes, that something is a rogue planet. Microlensing works because gravity bends space, and bent space bends light. When a rogue planet passes in front of a more distant star, the planet's gravity acts like a lens, focusing the star's light and making it appear brighter for a brief period. The magnification typically lasts a few days to a few weeks, depending on the planet's mass and speed. By carefully monitoring millions of stars, astronomers can detect these brief magnifications and infer the presence of rogue planets. Each detection is a glimpse of a world in transit, a planet drifting past a star, its presence revealed only by the subtle bending of light. Current estimates suggest there might be more rogue planets in the galaxy than stars. Billions of them, trillions perhaps. Cold worlds, Earth-sized or larger, drifting through the darkness in eternal night. The numbers are staggering. Our galaxy contains somewhere between 200 and 400 billion stars. If rogue planets are even more common, That means there could be hundreds of billions, perhaps trillions of worlds wandering the darkness between stars. That's more planets than there are grains of sand on all the beaches of Earth. Where do they come from? Most rogue planets are thought to be ejected from their solar systems during the chaotic early years of planetary formation. When a solar system is young, planets are still finding their orbits. Gravitational interactions between planets can lead to close encounters, where one planet slingshots another outward at high speed. If the ejected planet is moving fast enough, it escapes the star's gravity entirely and becomes a rogue. In some cases, the ejection might be gentle, the planet drifting slowly outward, taking millions of years to leave the system. In other cases, it might be violent, a close encounter flinging the planet outward at enormous speed, sending it hurtling into the void within years. Either way, the result is the same: a planet without a star, wandering alone through interstellar space. Could life exist on a rogue planet? It seems unlikely, but not impossible. If a planet had enough internal heat, perhaps from radioactive decay, and if it had a thick atmosphere to trap that heat, liquid water might exist beneath its frozen surface. Life, as we've learned, is remarkably tenacious. It finds ways. Consider a planet like Jupiter, ejected from its solar system while still warm from formation. Jupiter generates internal heat through gravitational contraction. It radiates more energy than it receives from the sun. A rogue Jupiter might continue generating heat for billions of years, keeping its moons warm even in the absence of starlight. Some of Jupiter's moons, Europa, Enceladus, Ganymede, are thought to have subsurface oceans, heated by tidal forces and radioactive decay. If a Jupiter-like planet were ejected with its moons still attached, those oceans might persist. And where there's liquid water, there might be life. It's speculation, of course. We don't know if life exists on any rogue planet. We don't even have direct images of them, just indirect detections through microlensing. But the possibility is tantalizing. Worlds drifting through the darkness, carrying life within them, utterly unknown to anyone. But even if life can't exist on rogue planets, they're still fascinating. They represent the universe's discards, worlds that didn't make the cut, ejected from their solar systems during the chaotic early years of planetary formation. And yet they persist. They don't disappear just because they're alone. There's a lesson there, perhaps, about endurance, about existing even when no one is watching, about the persistence of matter in a universe that often seems hostile to it. A rogue planet doesn't know it's alone. It doesn't feel lonely. It simply exists, drifting through space, following the laws of physics, indifferent to whether anyone notices. And perhaps that's the truest form of existence, being without needing acknowledgement, persisting without purpose, simply continuing because stopping is not an option. The rogue planets are out there, right now, as you listen to this. Billions of them, scattered through the galaxy, moving in random directions, never encountering anything. Cold, dark, silent worlds, existing in the void. And somewhere among them, who knows, there might be one that harbors life. A world with no sun, no seasons, no day or night. Just warmth from within, and an ocean beneath the ice, and organisms that have never seen a star. It sounds like science fiction. But the universe is stranger than fiction. And rogue planets are one of its strangest inhabitants. Segment 14. Diamond planets. Pressure beyond imagination. Under enough pressure, carbon becomes diamond, and in the universe, pressure is abundant. There are planets out there, former stars, compressed and cooled, that may contain interiors made largely of crystalline carbon, diamonds the size of continents, diamonds larger than Earth, and no one will ever mine them. They simply exist, glittering in the dark, monuments to what physics does when given enough time and force. The key to understanding diamond planets is pressure. On Earth, diamonds form deep in the mantle, where temperatures and pressures are high enough to force carbon atoms into a tight crystalline lattice. Natural diamonds require pressures of about 50,000 atmospheres, 50,000 times the pressure at Earth's surface, and temperatures of 1,000 to 1,300 degrees Celsius. Under these conditions, carbon transforms from graphite to diamond. In the universe, pressures far exceeding those found in Earth's mantle are common. The cores of giant planets, the interiors of white dwarfs, the crushing depths of neutron stars, all these environments experience pressures that dwarf anything on Earth. And where there's carbon and pressure, there might be diamond. One of the most famous candidates is 55 Cancri, a super-Earth located about 40 light-years away. Based on its mass and radius, astronomers believe its interior might contain significant quantities of carbon, potentially in diamond form. The pressure inside 55 Cancri is so immense that carbon atoms are forced into the crystalline structure we recognize as diamond. 55 Cancri is about twice the size of Earth and about 8 times as massive. It orbits its star so closely that a year there lasts just 18 hours. The intense radiation from the nearby star heats the planet's surface to extreme temperatures. Estimates suggest the day side might reach 2,400 Kelvin, hot enough to melt most metals. Despite these hellish conditions, the planet's interior might be a different story. Deep beneath the molten surface, pressures could be high enough to compress carbon into diamond. Not a single gem, but a layer, a shell of diamond thousands of kilometers thick, wrapping around the planet's core. But 55 Cancri isn't exactly a pleasant place. Its surface temperature exceeds 2,000 degrees Celsius. It's tidally locked to its star, meaning one side is in perpetual day and the other in perpetual night. Any diamonds on this world would be buried deep beneath a hellish surface, beautiful perhaps, but utterly inaccessible. And 55 Cancri is just one example. The universe might be filled with carbon-rich planets, each one potentially harboring diamond in its interior. Carbon is the 4th most abundant element in the universe, produced in vast quantities by dying stars. When a solar system forms, that carbon can become part of planets, and if the pressures are high enough, diamond. Some astronomers have speculated about planets made almost entirely of diamond, worlds where carbon dominates the composition and where the entire interior has been compressed into crystalline form. Such planets would be denser than Earth, with different geological properties. They might have diamond mountains, diamond continents, diamond cores, and then there are the remnants of dead stars. White dwarfs, the cooling cores of stars like our sun, are made of carbon and oxygen. Over trillions of years, far longer than the current age of the universe, these white dwarfs will cool and crystallize. Some astronomers believe that extremely old white dwarfs might contain vast diamond cores, crystallized remains of once burning stars. A diamond the size of a star. It sounds like fantasy, but the physics checks out. In 2004, astronomers announced the discovery of BPM 37093, a white dwarf located about 50 light-years away in the constellation Centaurus. Based on observations of the star's pulsations, they concluded that its interior had crystallized. It was, in essence, a diamond with a thin carbon atmosphere. The crystal core was estimated to weigh about 10 power 34 carats. That's a 1 followed by 34 zeros, a diamond of almost unimaginable size. The astronomers nicknamed it Lucy, after the Beatles' song Lucy in the Sky with Diamonds. It seemed fitting. A diamond floating in space, larger than Earth, cold and crystalline and eternal. As white dwarfs cool over time, their carbon interiors will crystallize. The oldest white dwarfs in the universe are already undergoing this process, their cores slowly transitioning from carbon gas to carbon solid. In the far future, when all the stars have died and the universe has grown cold and dark, these crystalline corpses will remain, diamonds drifting through the void, the final legacy of stars that once burned bright. And that's the strange thing about the universe. It produces objects that seem like they should be impossible, like they should exist only in fairy tales or science fiction novels. And then you do the math, and you realize, no, this is real. This is happening. Somewhere out there, there's a diamond the size of a world. We tend to think of diamonds as precious, as rare, as valuable. On Earth, they are. But in the universe, diamonds might be common, just inaccessible, buried in the cores of distant planets, locked in the hearts of dead stars, scattered throughout the cosmos in quantities that would dwarf all the diamonds ever mined on Earth. There's something humbling about that. Our precious gems, the objects we've fought wars over and proposed marriages with, are cosmic commonplaces. The universe makes them by the ton, by the trillion tons, without effort or intent. They're just what happens when carbon meets pressure, and they're beautiful, even if no one ever sees them, even if they exist forever in darkness. Buried beneath hellish surfaces or drifting through empty space, they're beautiful because they exist, because the laws of physics, applied consistently over billions of years, produce structures of crystalline perfection. The universe is an artist who doesn't know it's making art. It creates diamonds and nebulae and galaxies, not for anyone, but simply because that's what physics does. And we're fortunate enough to observe some of it, to calculate the existence of diamond planets, to detect the crystalline cores of white dwarfs, to imagine the beauty that exists in places we'll never visit. Tonight, consider the diamonds scattered throughout the cosmos. They're out there, right now, glittering in the dark, and they'll be there long after we're gone, monuments to pressure, to time, to the patient work of physics over eons. Segment 15, the Boomerang Nebula, the coldest known place. The coldest natural place ever observed in the universe is the Boomerang Nebula, located about 5,000 light-years from Earth in the constellation Centaurus. Its temperature is roughly 1 degree above absolute zero, colder than the background radiation left over from the Big Bang, colder than empty space itself, colder than anything else we've ever found in nature. To understand how remarkable this is, you need to understand what cold means at this scale. Temperature is really a measure of motion, the vibration and movement of atoms and molecules. The hotter something is, the faster its particles move. The colder something is, the slower they become. Absolute zero, 0 Kelvin, or about minus 273 degrees Celsius, is the point at which all motion would theoretically stop. Particles would freeze in place, perfectly still, with no energy left to give. Nothing in the universe has ever reached absolute zero. It's theoretically impossible. You'd need to remove every last bit of energy from every last particle. But the Boomerang Nebula comes extraordinarily close. At just 1 degree above absolute zero, the gas in this nebula is barely moving. Its atoms are nearly frozen, drifting with infinitesimal slowness through space. How is this possible? The Boomerang Nebula is what astronomers call a protoplanetary nebula, a transitional phase in the death of a star. At its center is a dying star, once much like our Sun, now in the final stages of its life. This star is expelling its outer layers into space, creating the nebula we observe. But unlike most dying stars, this one is losing mass at an extraordinary rate, about 100 times faster than typical. As the gas expands outward, it cools. This is the same principle that makes refrigerators work, the same reason aerosol cans feel cold when you spray them. When gas expands rapidly, it loses energy, and its temperature drops. In most nebulae, this cooling is modest. But in the Boomerang Nebula, the expansion is so rapid, the gas is moving outward at about 600,000 kilometers per hour, that the cooling is extreme. The result is a temperature lower than the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. This background radiation has a temperature of about 2.7 Kelvin, still incredibly cold by human standards, but warm compared to the Boomerang Nebula. Almost everywhere in the universe, this background radiation provides a kind of floor, a minimum temperature below which nothing can naturally go. The Boomerang Nebula broke through that floor. The nebula was first observed in 1995 by astronomers using the 15-meter Swedish ESO submillimeter telescope in Chile. They noticed something strange in their data. The nebula appeared to be absorbing the cosmic microwave background rather than simply existing against it. This could only happen if the nebula was colder than the background itself. It was an unexpected discovery, one that challenged assumptions about how cold natural objects could get. The nebula's name, incidentally, comes from its apparent shape when first observed with ground-based telescopes. It looked vaguely like a boomerang. But later, images from the Hubble Space Telescope revealed a more complex structure, two lobes of gas expanding outward from the central star, like a cosmic hourglass or a ghostly bow tie. The shape is beautiful and strange, a dying star breathing its last breath in two directions at once. If you could somehow stand in the Boomerang Nebula, which you couldn't, but imagine it anyway, your experience would be unlike anything possible on Earth. Every molecule of gas around you would be nearly motionless. Sound would barely propagate. There wouldn't be enough molecular motion to carry waves through the medium. Your thoughts, which depend on chemical reactions in your brain, would slow and stop. Chemistry itself would approach a halt. Life would be impossible. And yet, there's something peaceful about imagining it. A place where everything has slowed to a near standstill, where motion approaches zero, where the frantic activity of the universe, the burning of stars, the collision of galaxies, the endless churn of matter and energy has been reduced to stillness. The Boomerang Nebula is, in a sense, the universe's closest approach to perfect rest. Here on Earth, scientists have created temperatures even colder than the Boomerang Nebula. In laboratories, using lasers and magnetic fields to trap atoms and drain their energy. They've gotten to within billionths of a degree of absolute zero. But those are artificial conditions, maintained for fractions of a second in tiny volumes of space. The Boomerang Nebula is natural. It spans a light year across. It's a cold that exists without anyone creating it, a cold that the universe produced on its own. There's a philosophical dimension to extreme cold that's worth considering. Heat is activity, motion, change. Cold is stillness, slowness, preservation. In a very real sense, the Boomerang Nebula represents the universe's tendency toward stillness, the eventual fate of everything if you wait long enough. In the far future, trillions of years from now, all the stars will have burned out. All the galaxies will have faded. The universe will approach a state of maximum entropy, minimum energy, near absolute cold. Everything will be as cold as the Boomerang Nebula, or colder. That future is so distant that it barely matters to us now, but the Boomerang Nebula offers a preview. It shows us what stillness looks like, what happens when the universe runs out of energy. And somehow, that's not frightening. It's quiet. It's peaceful. It's an end without violence, without drama, just a slow fading into darkness and rest. Tonight, as you lie here, you are warm. Your body is a small engine of heat, burning energy to maintain its temperature. The contrast between you and the Boomerang Nebula couldn't be greater, and yet, you're both part of the same universe. You're both made of the same atoms. Someday, the atoms in your body will cool and scatter and become part of something else. Perhaps something cold. Perhaps something warm. The cycle continues. For now, just notice your own warmth. It's a gift from the stars, from nuclear fusion, from the sun, from the food you've eaten, and the processes that converted it into energy. You are a small pocket of heat in a universe that tends toward cold. Cherish that. It won't last forever. But then again, nothing does. Segment 16. The hottest known place, a supernova core. At the opposite extreme from the Boomerang Nebula, let's talk about heat. Not the warmth of a summer day, not even the heat of the sun's surface. We're talking about temperatures so extreme that they redefine what matter can be. The hottest known place in the universe, at least the hottest we've been able to measure or calculate with confidence, is the core of a collapsing massive star. In the moments just before it explodes as a supernova, temperatures there reach hundreds of billions of degrees. That's not a typo, hundreds of billions. To put that in perspective, the center of our sun is about 15 million degrees Celsius. A supernova core is hotter by a factor of tens of thousands. It's a heat so intense that it exists in a category all its own. At these temperatures, the normal rules of chemistry become meaningless. Atoms can't exist in any recognizable form. Electrons are stripped away from nuclei instantly. Protons and neutrons begin to break down into their constituent quarks. What you have isn't gas or plasma in the usual sense. It's a seething soup of fundamental particles, crushed together at densities that defy imagination. To understand how this happens, you need to understand how massive stars die. Throughout their lives, stars like our sun fuse hydrogen into helium in their cores. The energy released by this fusion creates outward pressure that balances the inward pull of gravity. But massive stars, those with 8 or more times the mass of the sun, don't stop at helium. They fuse helium into carbon, carbon into oxygen, oxygen into silicon, and silicon into iron. Each stage releases energy. Each stage maintains the balance, but iron is a dead end. Fusing iron doesn't release energy. It requires energy. When the core of a massive star becomes iron, fusion stops. And without fusion's outward pressure, there's nothing to resist gravity. The core collapses. This collapse happens in less than a second. The core, an object about the size of Earth but containing more mass than the sun, falls inward at nearly a quarter the speed of light. As it collapses, it compresses and heats. Temperatures skyrocket into hundreds of billions of degrees. Densities reach levels where atomic nuclei are crushed together into a solid mass of neutrons. The collapse only stops when this neutron matter becomes so dense that it can't compress any further. Thanks to a quantum mechanical effect, called neutron degeneracy pressure. At the moment of maximum compression, the core rebounds slightly. This rebound sends a shock wave outward through the star's outer layers. Meanwhile, the collapsed core emits a flood of neutrinos, ghostly particles that interact so weakly with matter that they pass through almost everything. These neutrinos carry away enormous amounts of energy, and some of that energy is deposited in the outgoing shock wave. The shock wave accelerates, punching through the star's outer layers and blasting them into space. The result is a supernova, an explosion so bright that it can outshine an entire galaxy for weeks. The outer layers of the star are scattered across light years of space, carrying with them the heavy elements forged during the star's lifetime. What remains at the center is either a neutron star, a city-sized ball of neutrons, spinning rapidly and sometimes producing pulses of radiation, or, if the original star was massive enough, a black hole. All of this happens in seconds. The core collapse takes less than a second. The rebound and shockwave propagation take hours. By the time the light reaches us, the most dramatic events are already over. We see the aftermath, not the cause. This is why we can't observe supernova core temperatures directly. The core is hidden inside the star, and by the time the explosion becomes visible, the core has already collapsed into something else. But we can infer what happened based on the physics we understand. We can model the collapse on supercomputers, calculating temperatures and densities at each stage. And we can observe the neutrinos emitted during the collapse, as we did in 1987, when a supernova in the Large Magellanic Cloud produced a burst of neutrinos detected on Earth about 3 hours before the visible light arrived. Those neutrinos confirmed our models. They told us that the core really did collapse, that the temperatures really did reach the extremes we calculated. The universe's most violent laboratories are also its most hidden ones, and yet we've found ways to peer inside them. There are other hot places in the universe, of course. The cores of quasars, where matter spirals into supermassive black holes, reach temperatures of billions of degrees. Neutron star collisions, when two stellar corpses spiral together and merge, produce similar extremes. In laboratories on Earth, particle accelerators create momentary temperatures even hotter than supernova cores, trillions of degrees, for infinitesimal fractions of a second. Scientists at the Large Hadron Collider have created conditions similar to those just after the Big Bang, when the universe was a tiny fraction of a second old. But supernova cores remain special because they occur in nature at enormous scales, producing real effects that ripple across the universe. The heavy elements in your body, the gold in any jewelry you might wear, the iodine in your thyroid, the uranium deep in the earth, were all forged in these extreme environments. The heat of a supernova core is the fire in which the ingredients of worlds are made. There's something almost cleansing about that much heat. Nothing survives it in its original form. Every structure is broken down into fundamental components. Every bond is severed. Matter is reduced to its simplest possible state, individual quarks and particles, bouncing off each other at incredible speeds, ready to recombine into something new. And recombine, they do. As the supernovas ejecta cool and expand, atoms form once again. Nuclei capture electrons, molecules assemble. Over millions of years, this scattered material drifts through space, eventually becoming part of new nebulae, new stars, new planets. The heat didn't just destroy, it created. It forged new elements that wouldn't exist otherwise. It scattered those elements across the cosmos, seeding future worlds with the building blocks of complexity. This is the paradox of extreme heat. It is both destructive and generative. The same process that annihilates matter also enables the creation of new matter. The universe burns so that it can build. It destroys so that it can begin again. And the cycle continues over and over for billions of years. Tonight, as you rest in the comfortable warmth of your room, consider the extremes that made your existence possible. Somewhere, billions of years ago, a massive star collapsed. Its core reached temperatures beyond comprehension, and in that inferno, the atoms that would eventually become you were forged. You carry that heat inside you. Not literally, of course, but in the history of your matter. You are the product of the universe's most violent moments, cooled and assembled and given consciousness. There's something profound about that, something that connects you to events so ancient and so extreme that they seem to belong to a different reality altogether. And yet, here you are, a thinking being made of stardust and supernova ash, resting quietly in the dark. The universe is not gentle. It produces extremes that would annihilate anything we know. But from those extremes, it also produces us. And that's worth remembering on nights like this. On segment 17, white dwarfs, the long, slow fade. When a star like our sun exhausts its fuel, it doesn't explode. It's not massive enough for that. The violence of supernovae is reserved for giants, stars 8 times the sun's mass or more. Smaller stars meet a gentler fate. They swell, they shed, and then they contract into something small and patient, a white dwarf. The process begins when the star runs out of hydrogen in its core. For billions of years, our sun has been fusing hydrogen into helium, releasing energy that keeps it shining. But eventually, the hydrogen runs low. The core contracts and heats up, and fusion begins in a shell around the core. The star swells into a red giant, expanding to enormous size. When our sun becomes a red giant, it will engulf Mercury, Venus, and possibly Earth. This red giant phase doesn't last long, cosmically speaking. A few 100 million years, perhaps. The star sheds its outer layers into space, creating a beautiful shell of glowing gas called a planetary nebula. At the center of this nebula is the star's exposed core, hot, dense, and small. This core is the white dwarf. A white dwarf is approximately the size of Earth, but contains nearly the mass of the Sun. That means its density is extraordinary, about 1 million times denser than water. A teaspoon of white dwarf material would weigh several tons. If you could somehow stand on a white dwarf surface, the gravity would be about 100,000 times stronger than on Earth. You would be crushed instantly. What keeps a white dwarf from collapsing further? The answer is quantum mechanics. At such extreme densities, electrons are packed so closely together that they resist further compression, a phenomenon called electron degeneracy pressure. This pressure has nothing to do with temperature or energy. It's a fundamental property of electrons, which refuse to occupy the same quantum state. The white dwarf is supported not by nuclear fusion, not by heat, but by the stubbornness of electrons. And because fusion has stopped, the white dwarf is no longer producing new energy. It's simply glowing with leftover heat, like an ember after a fire has gone out. It will glow for a very, very long time. How long? The calculations are humbling. A white dwarf takes trillions of years to cool completely. Trillions. The current age of the universe is only about 13.8 billion years. That's billion with a B. A trillion is 1,000 billion. We're talking about timescales so vast that our current cosmic age is just a tiny fraction of them. No white dwarf has ever finished cooling. The universe simply hasn't existed long enough. Every white dwarf we observe is still glowing, still radiating its stored heat into space. They're all in the early stages of a cooling process that will take longer than everything that has happened since the Big Bang. In the far, far future, so far that it makes our current cosmic age look like the first second of a new year, white dwarfs will finally fade into darkness. They'll become what astronomers theoretically call black dwarfs. Cold, dark, dead husks of stars, invisible to everything except gravity. They'll still have mass, still curve space around them, but they'll emit no light, no heat, nothing. They'll be the ultimate stellar corpses, preserved in the void forever. But that future hasn't arrived yet. For now, and for trillions of years to come, white dwarfs persist. They don't do much. They don't explode or pulse or emit jets of radiation like more dramatic objects. They just exist, slowly cooling, slowly fading, taking their time. There's something almost zen about them. They've finished their active lives. They've accepted their fate. They're not in a hurry. The closest white dwarf to Earth is Sirius B, the companion of the bright star Sirius. It's located about 8.6 light-years away. Sirius B is smaller than Earth, but contains almost as much mass as the Sun. When it was first discovered in the 19th century, astronomers were puzzled. How could something so small be so massive? It wasn't until the 20th century, with the development of quantum mechanics, that we understood the answer. White dwarfs come in different varieties, depending on the composition of the original star. Most are made primarily of carbon and oxygen, the elements produced by helium fusion in the star's later life. Some are made of oxygen and neon. A few born from very low-mass stars might be made of helium alone. The composition affects the white dwarf's cooling rate and its eventual fate. As a white dwarf cools, something remarkable happens. At a certain temperature, still hot by human standards, but cool by stellar standards, the carbon and oxygen in its core begin to crystallize. The white dwarf is literally turning into a giant crystal, a cosmic diamond forming in slow motion over billions of years. Astronomers have detected evidence of this crystallization in some white dwarfs, observing the subtle effects it has on their cooling and pulsation. This connects back to an earlier segment where we discussed diamond planets. But there's something even more poetic about a white dwarf crystallizing. It was once a star like our sun, burning, shining, giving warmth to whatever planets orbited it, and now it's slowly becoming a jewel. The fire has gone out, and what remains is transforming into crystal. It's as if the star is leaving behind a memorial to itself, a permanent record of what it once was. There's another fate that awaits some white dwarfs, one that's more dramatic. If a white dwarf is part of a binary system, orbiting close to another star, it can accumulate matter from its companion. Hydrogen and helium stream across from the companion star, piling up on the white dwarf's surface. Eventually, the accumulated material becomes hot and dense enough to ignite in nuclear fusion. The result is a nova, a sudden brightening as the stolen material burns on the white dwarf's surface. Unlike a supernova, a nova doesn't destroy the star. The white dwarf survives, and the cycle can repeat. Some white dwarfs have experienced dozens of novae over the centuries, flaring up periodically as they consume material from their companions. But if a white dwarf accumulates enough mass, approaching a limit called the Chandrasekhar limit, about 1.4 times the mass of the Sun, something more catastrophic happens. The electron degeneracy pressure that supports the white dwarf is no longer sufficient. The white dwarf collapses, triggering runaway nuclear fusion that consumes the entire star in seconds. The result is a Type Ia supernova, one of the most powerful explosions in the universe. Type Ia supernova are important to astronomers because they all have roughly the same brightness. This makes them excellent standard candles for measuring cosmic distances. By observing type Ia supernovae in distant galaxies, astronomers can calculate how far away those galaxies are. This technique was crucial in the discovery that the universe's expansion is accelerating, one of the most surprising findings in modern cosmology. So white dwarfs, despite their quiet nature, are central to our understanding of the cosmos. They help us measure the universe. They show us what stellar death looks like. They demonstrate quantum mechanics operating on astronomical scales. And they offer a glimpse of the far future, when all stars will have faded and only cooling remnants remain. Our own sun will become a white dwarf someday, about 5 billion years from now. It will shed its outer layers, creating a planetary nebula that might be visible from distant stars. And then it will contract into a small, dense core, glowing faintly with the heat of its former life. That white dwarf will persist for trillions of years, long after Earth is gone. Long after the Milky Way has merged with Andromeda. Long after most of the stars in the universe have burned out. It will be a quiet memorial to the star that once gave us life, a faint ember in an increasingly dark cosmos, and eventually, even that ember will go out. The white dwarf will cool into a black dwarf, invisible and cold, drifting through the void forever, but eventually is so far away that it's almost meaningless. We're talking about timescales that dwarf everything in human experience, everything in cosmic history so far. For now, the sun still shines, and we're here to witness it. Tonight, as you feel yourself drifting towards sleep, consider the patience of white dwarfs. They don't rush. They don't struggle against their fate. They simply exist, cooling gradually, taking trillions of years to complete a process that has no urgency. There's wisdom in that, perhaps. In a universe of violence and extremes, white dwarfs represent something gentler. The slow fade, the gradual release, the long exhale at the end of a stellar life. We could learn from them. We often rush through our days, anxious about the future, impatient for things to happen. But the universe doesn't share our urgency. It operates on timescales that make our entire lives look like a single heartbeat. White dwarfs will still be cooling long after every human ambition has been forgotten. Every human fear has dissolved, and that's okay. We don't need to last forever to matter. We don't need to burn as long as the stars. We just need to be here, now, experiencing whatever we can while we can. The white dwarfs will handle the rest. Let yourself relax. Let your thoughts slow down. Let the patience of the cosmos wash over you, quiet and endless, stretching toward a future you'll never see. Segment 18. Stellar Nurseries. Where stars are born, stars don't appear from nowhere. They don't simply blink into existence like lights being switched on. They're born, slowly, patiently, over millions of years, inside vast clouds of gas and dust called nebulae. These are the stellar nurseries of the universe, and they are among the most beautiful and mysterious places in existence. Picture a cloud, not the fluffy white kind drifting across a summer sky, but something far larger, something that stretches across dozens or even hundreds of light years. A cloud so vast that light itself takes years to cross from one side to the other. Inside this cloud, there is hydrogen, the simplest element, the most abundant substance in the universe, along with traces of helium, dust, and heavier elements left behind by stars that died long ago. For most of its existence, the cloud simply drifts. It's cold, just a few degrees above absolute zero, and diffuse, with particles separated by distances that would feel like emptiness to anything human-sized. If you could somehow float inside one of these clouds, you'd see almost nothing. The dust would block distant starlight. The gas would be invisible. You'd be surrounded by darkness, by silence, by the patient waiting of matter that doesn't yet know what it will become. But then something changes. Perhaps a nearby star explodes, sending shockwaves rippling through the cloud. Perhaps the cloud drifts too close to the gravitational influence of a passing galaxy or cluster. Perhaps it simply reaches a critical density through its own slow contraction. Whatever the trigger, parts of the cloud begin to collapse inward. Gravity, the most patient force in the universe, starts to work. And once gravity gets started, it doesn't stop. The collapsing region grows denser. As it contracts, it heats up, a fundamental property of physics that you've experienced yourself every time you've pumped air into a bicycle tire and felt the pump grow warm. The center of the collapse becomes hotter and hotter. Pressure builds. The cloud fragment begins to spin, flattening into a disk as it rotates faster and faster, like pizza dough being tossed by an invisible chef. At the center of this disk, a protostar forms. It's not yet a true star, fusion hasn't begun, but it's glowing with the heat of its own contraction. It might take 100,000 years for this protostar to gather enough mass to achieve enough pressure at its core for the next step to occur. And then, finally, it happens. The core temperature reaches about 10 million degrees Celsius. At this temperature, hydrogen atoms are moving so fast, slamming into each other so violently that they overcome their natural electromagnetic repulsion and fuse together. Hydrogen becomes helium. Mass converts to energy according to Einstein's famous equation, and a star is born. There's no explosion at this moment, no fanfare, no cosmic announcement. The universe doesn't pause to acknowledge what just happened. The star simply begins to shine, and will continue shining for millions or billions of years, depending on its mass. One moment, there was a collapsing cloud. The next, there was a sun. Meanwhile, the leftover material in the disk, the gas and dust that didn't fall into the star, begins its own slower transformation. Dust grains collide and stick together, forming larger and larger clumps. Pebbles become boulders. Boulders become planetesimals, rocky bodies a few kilometers across. And over millions of years, these planetesimals collide and merge to form planets. This is how our own solar system formed about 4.6 billion years ago. The sun ignited at the center of a collapsing cloud. Earth coalesced from the debris around it. And eventually, on one of those planets, chemistry became biology, biology became consciousness, and here you are, lying in bed, listening to a story about your own distant origins. The Orion Nebula is perhaps the most famous stellar nursery visible from Earth. You can see it with the naked eye as a faint smudge in the constellation Orion, just below the 3 stars of Orion's belt. Through a telescope, it transforms into something breathtaking. Swirling clouds of gas, pillars of dust, newborn stars illuminating the surrounding material with ultraviolet light. Inside the Orion Nebula, right now, stars are forming. Solar systems are taking shape. Future planets are beginning their slow assembly. Somewhere in that cloud, there might be a world that will one day harbor life. Beings who will look up at their own night sky and wonder where they came from. And they'll have the same answer we do. From a cloud. From dust and gas and gravity. from the patient work of physics over millions of years. The Carina Nebula, the Eagle Nebula, the Lagoon Nebula. These are just a few of the stellar nurseries scattered across our galaxy. Each one is a factory of stars producing new suns at rates that vary from a few per million years to dozens per million years in the most active regions. Our galaxy alone produces perhaps 1 to 3 new stars per year, on average. Not many compared to the hundreds of billions already shining, but enough that the galaxy is constantly renewing itself. And every galaxy does this. Across the observable universe, in hundreds of billions of galaxies, stellar nurseries are operating. New stars are being born. New solar systems are forming. The universe is not static. It's alive in a sense. Not alive the way you and I are alive, but changing, growing, producing new things from old materials. It's recycling. The atoms in your body were once inside a star. That star died, scattered its material into space, and that material was gathered up by a new stellar nursery. It formed our sun, our planets, our oceans, our cells. And someday, billions of years from now, those atoms will be scattered again, gathered again, and formed into something new. You are not separate from this process. You are part of it. You are one of its products, and eventually, you will be one of its ingredients. But that's a very long time from now. Tonight, you're just here, warm and safe, thinking about clouds of gas giving birth to stars. And somewhere out there, in some nebula you'll never see, a new sun is igniting for the first time. Let's drift onward. Segment 19, the oldest known star, Methuselah. There's a star called Methuselah, located about 190 light-years from Earth, that appears to be nearly as old as the universe itself, roughly 13.7 billion years old, which means it formed when the cosmos was young, so young that galaxies were still assembling, that the first generation of stars was just beginning, that the universe we know today was barely a rough draft. For context, the universe is about 13.8 billion years old. Methuselah is almost that old. It has existed for nearly the entire history of everything. When it first began to shine, there was no Milky Way, not in the form we know it. The cosmic web was still taking shape. Supermassive black holes were still growing at the centers of proto-galaxies. The heavy elements we take for granted, carbon, oxygen, iron, existed only in trace amounts, if at all. Methuselah is what astronomers call a metal-poor star. In astronomy, metals refers to anything heavier than hydrogen and helium, a confusing terminology that has frustrated chemistry students for decades. Methuselah's composition is almost entirely hydrogen and helium, with only the faintest traces of heavier elements. This is a signature of extreme age. Here's why. The first stars in the universe formed from the primordial gas left over from the Big Bang, almost pure hydrogen and helium. These first stars were massive, short-lived, and violent. They burned through their fuel quickly and exploded as supernovae, scattering heavier elements into the surrounding space. The next generation of stars incorporated these elements, and each subsequent generation was enriched further. Our sun, for example, is a relatively young star, only about 4.6 billion years old, and it contains a healthy proportion of heavy elements: iron, silicon, oxygen, carbon, all the ingredients that eventually became planets and moons and, eventually, living things. But Methuselah formed before most of those enrichment cycles occurred. It's a fossil from an era when the universe was still chemically primitive. Looking at Methuselah is like looking at a photograph from the cosmos's infancy. The star has survived everything. It has witnessed the formation of the Milky Way, the the gradual accumulation of smaller galaxies and clouds of gas into the spiral structure we know today. It has seen the birth and death of countless other stars, stars that lived fast and died young, scattering their material into space so that new generations could form. It has orbited the galactic center hundreds of times, drifting through different neighborhoods, passing through spiral arms and out again. And through all of that, it has simply continued burning, fusing hydrogen into helium, one atom at a time, with the patience of something that has nowhere else to be. Methuselah is not a dramatic star. It's not massive or bright. It's what astronomers call a subgiant, a star that has begun to exhaust the hydrogen in its core and is slowly transitioning toward the next phase of its life. In a few billion years, it will swell into a red giant, shed its outer layers, and collapse into a white dwarf. And then, it will spend trillions more years cooling, fading, approaching, but never quite reaching the final darkness. But for now, it just shines. A faint point of light in the constellation Libra, visible only through telescopes, unremarkable to anyone who doesn't know its history. There's something almost miraculous about Methuselah's survival. The universe is violent. Stars explode. Galaxies collide. Black holes consume. Gamma ray bursts sterilize entire regions of space. And yet, this one star, this quiet, ancient, metal-poor star, has endured. It has outlasted empires that never existed, civilizations that never rose, planets that formed and were destroyed. It was shining before Earth existed. It will probably still be shining long after Earth is gone. The name Methuselah comes from the Hebrew Bible, where Methuselah is the oldest person mentioned, said to have lived 969 years. That's impressive for a human, but nothing compared to 13.7 billion years. The star has outlived its namesake by a factor of more than 14 million. And here's the strange part. When Methuselah's age was first calculated, it appeared to be older than the universe itself. This was a measurement error, of course. Our estimates of both the star's age and the universe's age have uncertainties. But it raised an amusing possibility. What if we'd found a star that predated existence? What if our understanding of the universe was fundamentally wrong? We refined the measurements. The ages now agree, within the margins of error. Methuselah is very old, but not older than the cosmos. The universe's timeline is intact, but the episode is a reminder of how much we still don't know. Our measurements are always approximate. Our models are always incomplete. The universe tolerates our curiosity, but it doesn't give up its secrets easily. Tonight, if you wanted to, you could point a telescope at the constellation Libra and find Methuselah. It wouldn't look special, just a faint star among many. But now you know what it is. A survivor, a witness to nearly everything, a quiet light that has been burning since the beginning. There's comfort in that somehow, proof that things can last, that even in a universe characterized by change and violence, some objects persist, some things endure. Let's keep moving. Segment 20. Uy-Scuti, one of the largest known stars. Uy-Scuti is so large that our usual vocabulary for describing stars starts to feel inadequate. We say it's big, but that doesn't capture it. We say it's massive, but that's actually misleading. It's not particularly massive, just incredibly voluminous. We say it's enormous, colossal, gargantuan, and none of these words really work. Uy-Scuti is simply larger than anything you've ever imagined a single object could be. If you placed Uy-Scuti where our sun currently sits, its surface would extend past the orbit of Jupiter. Not to Jupiter, past it. The orbits of Mercury, Venus, Earth, and Mars, all of them would be inside the star. You wouldn't need a spacecraft to visit UY Scuti. You'd already be there. You'd already be inside it. Let's try some numbers. UY Scuti has a radius roughly 1,500 times that of our Sun. If you could somehow drive a car around its equator at highway speeds, say 100 kilometers per hour, the trip would take about 3,000 years. Light, which normally takes just 4.6 seconds to travel around the Sun, takes about 8 hours to complete the same journey around UY Scuti. 8 hours, at the speed of light. The volume of UY Scuti is so large that you could fit approximately 5 billion suns inside it. 5 billion. That's roughly the same as the number of years of life remaining in our Sun. You could fill UY Scuti with a sun for every year our star has left to shine, and you'd still have room for more. And yet, for all its size, UY Scuti is surprisingly dim. Not compared to our Sun, it's about 340,000 times more luminous than the Sun, but compared to other stars of its type. The reason is temperature. UY Scuti's surface is cool as stars go, only about 3,000 Kelvin compared to the Sun's 5,800 Kelvin. This coolness gives it a deep red color, a ruddy glow that would be beautiful if you could ever see it from a safe distance. UY Scuti is what astronomers call a red supergiant. These are stars in the final stages of their lives, bloated and diffuse, slowly exhausting the last of their nuclear fuel. They're like aging giants who have expanded as they've aged, their outer layers spreading outward, even as their cores contract and heat up. The process goes something like this. A massive star spends most of its life fusing hydrogen into helium in its core, just like our Sun. But massive stars burn through their fuel much faster. When the hydrogen runs out, the core contracts and heats up, and the star begins fusing helium into carbon. The outer layers, meanwhile, expand dramatically. The star swells into a giant, then a supergiant. This expansion continues as the star burns through heavier and heavier elements. Helium becomes carbon, carbon becomes neon, neon becomes oxygen, oxygen becomes silicon. Each stage is shorter than the last. And finally, when silicon fuses into iron, the process stops. Iron fusion doesn't release energy, it consumes it. The core suddenly loses its support against gravity and collapses in less than a second. The result is a supernova, one of the most violent events in the universe. The core becomes a neutron star or black hole. The outer layers are blasted into space at a significant fraction of the speed of light, and a star that once took up more volume than Jupiter's orbit is reduced to an object the size of a city. UY Scuti has perhaps 1 million years left, maybe less. That sounds like a long time, but in stellar terms, it's a heartbeat. The star has already lived most of its life. What remains is the final chapter, the slow swelling, the gradual exhaustion, the inevitable collapse. But for now, it just exists. A bloated giant, glowing red, slowly pulsating as layers of gas rise and fall on its surface. If you could watch it over months, you'd see its brightness fluctuate by about 2 magnitudes, dimming and brightening as the outer layers expand and contract. It breathes in a way, not like a living thing, but rhythmically, cyclically, with a pattern that speaks to the complex physics happening inside. There's something almost melancholy about red supergiants. They're the end stage of something that was once vigorous and bright. They're dying in slow motion, stretched thin, held together only by gravity and the remnants of nuclear fire. And yet, they're beautiful. Their colors are striking, deep reds and oranges that dominate the spectra of infrared telescopes. They're proof that endings can be as spectacular as beginnings. UY Scuti isn't the only red supergiant, of course. Betelgeuse, in the constellation Orion, is another famous example, closer to us, and therefore easier to study. When Betelgeuse eventually explodes, it will be visible during the day, a new star suddenly appearing in Earth's sky. But UY Scuti is farther away, about 9,500 light-years, so its explosion, when it comes, will be less dramatic from our perspective. Not that it will be any less significant. A supernova is a supernova. When UY Scuti dies, it will seed the surrounding space with heavy elements. Some of those elements will become part of new stars, new planets, perhaps new life. The death of UY Scuti will be a beginning as much as an ending. Size in the universe does not always mean power. Sometimes it just means the end is coming slowly. UY Scuti is preparing for death in the grandest way possible, by becoming as large as it can before the final collapse. And somewhere, 9,500 years in the future, the light from that collapse will finally reach Earth. Perhaps someone will be watching. Perhaps they'll think of this moment, the time when the star was still bloated and red, still breathing, still alive. Let's keep drifting. Your segment 21, the cosmic web. The skeleton of everything. Galaxies are not scattered randomly across the universe. They're not sprinkled like dust on a table or distributed evenly like points on a grid. Instead, they're arranged in a vast, intricate structure that spans billions of light years. A structure so large and so complex that it took us decades to recognize it for what it was. We call it the cosmic web, and it is, quite literally, the skeleton of everything. Picture a spider's web, the kind you might find stretched between bushes on a dewy morning. Now imagine that web extended in 3 dimensions, filling a space the size of a room. Each strand represents a filament of galaxies, millions of galaxies strung together like pearls on a cosmic thread. Each intersection represents a node, a galaxy cluster, where thousands of galaxies gather in gravitational embrace, and each space between the strands represents a void, a vast, empty region where galaxies are rare and silence reigns. Now imagine that web scaled up to fill the observable universe, billions of light years across, containing hundreds of billions of galaxies, with filaments that take millions of years to traverse even at the speed of light. That's the cosmic web. You're inside it right now. Our Milky Way galaxy sits on a filament, part of a larger structure called the Laniakea supercluster. We're connected, through gravity and through the web's architecture, to thousands of other galaxies. We're part of a community, a cosmic neighborhood, even if we'll never visit our neighbors. The cosmic web formed from the same primordial fluctuations that shaped everything else in the universe. In the moments after the Big Bang, the cosmos was almost perfectly uniform, but not quite. There were tiny variations in density. Quantum fluctuations stretched to cosmic scales by the rapid expansion of the early universe. These fluctuations became the seeds of all structure. Regions with slightly higher density had slightly stronger gravity. They attracted more matter from their surroundings. Regions with slightly lower density lost matter to their neighbors. Over billions of years, this simple process, gravity pulling matter from low-density regions to high-density regions, created the web we see today. Dense regions became filaments, denser regions became nodes, and the spaces between them emptied out, becoming the vast voids that now stretch for hundreds of millions of light years. It's a bit like watching water drain from a bathtub. The water doesn't drain uniformly. It flows toward the drain, leaving some areas empty before others. The cosmic web is the universe draining toward gravity's pull, with filaments as the channels and voids, as the empty spaces left behind. What are these filaments made of? Mostly dark matter, the invisible substance that makes up about 27% of the universe and interacts with normal matter only through gravity. The dark matter forms the scaffolding, the skeleton of the web. Normal matter, the atoms that make up stars and planets and people, follows the dark matter, settling into the same structures, glowing where the dark matter is densest. This is why we can see the cosmic web, even though most of it is invisible. The galaxies, the stars, the gas clouds, they trace the underlying dark matter structure like lights on a Christmas tree reveal the shape of the branches. The visible universe is a decoration on an invisible framework, and the web is still evolving. Gravity is still pulling galaxies along the filaments toward the nodes. Matter is still flowing, slowly, from the voids into the denser regions. The web is becoming more pronounced, more defined, more web-like with each passing eon. In the far future, billions of years from now, the expansion of the universe will begin to dominate over gravity on large scales. The cosmic web will start to stretch and thin. Filaments will become more diffuse. Galaxies will drift away from each other, even as they cluster more tightly in local regions. The web will become a network of isolated islands, separated by ever-growing voids. Eventually, trillions of years from now, the expansion will carry distant galaxies beyond our cosmic horizon. They'll become invisible, not because they've disappeared, but because their light can no longer reach us. The universe will seem smaller, lonelier. The web will have unraveled, but that's an unimaginably long time from now. Tonight, the web is intact. The filaments stretch across the cosmos like the threads of some vast, patient tapestry. The galaxies cluster and shine. And you, made of atoms that once drifted on those filaments, that once gathered in those nodes, that once participated in the cosmic flow, you lie here, warm and safe, connected to everything. There's a strange comfort in the cosmic web. It means we're not isolated. We're not floating alone in empty space. We're part of a structure, a community of galaxies, a network of matter and energy and gravity that spans the universe. We're small, yes, insignificant probably, but we're connected. We belong to something larger than ourselves. Let's keep moving. Segment 22, Dark Matter, the Invisible Scaffolding. Roughly 27% of the universe is made of something we cannot see, cannot touch, and cannot detect directly. It doesn't emit light. It doesn't absorb light. It doesn't interact with normal matter through any force except gravity. We call it dark matter, and after decades of searching, we still don't know what it actually is. This might be one of the strangest facts in all of science. The majority of the matter in the universe is invisible to us, not hidden behind clouds of dust, not too far away to observe, simply invisible, passing through our telescopes, our detectors, our bodies, without leaving a trace. We are surrounded by something we cannot perceive. How do we know it's there? The same way you might know there's wind even with your eyes closed, by its effects. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma Cluster, a dense gathering of over 1,000 galaxies. He measured how fast the galaxies were moving and calculated how much gravity would be needed to hold the cluster together. The answer didn't make sense. The galaxies were moving too fast. There wasn't enough visible matter, stars, gas, dust, to provide the necessary gravity. The cluster should have flown apart long ago. Zwicky proposed that there must be invisible matter, dunkle Materie in German, providing the extra gravity. He was right, though it took decades for the scientific community to accept it. In the 1970s, astronomer Vera Rubin made similar observations of individual galaxies. She found that stars in the outer regions of galaxies were orbiting faster than they should be, based on the visible matter alone. Again, something invisible was providing extra gravity. Again, dark matter was the answer. Today, the evidence for dark matter is overwhelming. We see its effects everywhere we look, in the rotation of galaxies, in the movement of galaxy clusters, in the bending of light around massive objects, in the ripples of the cosmic microwave background. Dark matter is not a fringe hypothesis. It's a cornerstone of modern cosmology, and yet we don't know what it is. The leading hypothesis is that dark matter consists of particles, specifically a type of particle that interacts through gravity but not through the electromagnetic force or the strong nuclear force. These hypothetical particles are called WIMPs, weakly interacting massive particles. If they exist, they should occasionally bump into normal atoms, creating tiny, detectable signals. So we've built detectors. Deep underground, shielded from cosmic rays and other interference, scientists have placed tanks of ultra-pure liquids, waiting for dark matter particles to collide with atoms and produce a flash of light or a tiny recoil. We've waited for years. We've searched with increasing sensitivity. So far, nothing. This is frustrating, but it's also exciting. Every null result tells us something. It rules out certain types of particles, certain mass ranges, certain interaction strengths. The space of possibilities is shrinking. Either dark matter particles are more elusive than we thought, or there's something entirely different from what we expected. Some physicists are beginning to wonder if dark matter is not a particle at all. Perhaps it's a modification of gravity, a change to Einstein's equations that only becomes apparent on galactic scales. Perhaps it's something even stranger: primordial black holes, axions, sterile neutrinos, or something we haven't imagined yet. The honest answer is, we don't know, and that's okay. Science is not about having all the answers. It's about asking better questions. Dark matter is one of the best questions we've ever asked. What we do know is what dark matter does. It provides the gravitational framework for the cosmic web. It held galaxies together when they were young and fragile. It guided the formation of the first stars and the first structures. Without dark matter, the universe would look completely different, probably emptier, with fewer galaxies and less complex structures. In a sense, dark matter is the architect of everything you see in the night sky. The galaxies, the clusters, the cosmic web, all of it was shaped by the invisible hand of dark matter's gravity. We're living in a house designed by something we've never seen. There's something humbling about that. We like to think we understand the universe. We've mapped distant galaxies, decoded the cosmic microwave background, traced the evolution of the cosmos from the Big Bang to today. And yet, the majority of the matter in the universe remains invisible to us. We're seeing only part of the picture, perhaps a small part. What else are we missing? What other invisible threads run through reality, shaping it in ways we haven't detected? What secrets are hiding in plain sight, waiting for the right instrument or the right idea to reveal them? Tonight, as you lie here, dark matter is passing through you. Right now, billions of particles perhaps, streaming through your body without interacting, without leaving any trace. You'll never feel them. You'll never detect them. But they're there, part of the invisible universe that surrounds and permeates everything you know. Let's keep drifting. Segment 23. Dark energy, the force pulling everything apart. The universe is expanding. This is one of the most fundamental discoveries of the 20th century. the realization that space itself is stretching, carrying galaxies apart from each other like raisins in rising bread dough. The farther away a galaxy is, the faster it appears to be receding. This is Hubble's law, and it's been confirmed by countless observations over the past century. But here's what doesn't make sense. The expansion is speeding up. When astronomers first measured the expansion of the universe, they expected it to be slowing down. After all, gravity is attractive. It pulls things together. The mutual gravitational attraction of all the matter in the universe should be decelerating the expansion, like a ball thrown upward, gradually losing speed. In 1998, two teams of astronomers set out to measure this deceleration by observing distant supernovae, exploding stars whose brightness can be used to calculate their distance. They expected to find that the expansion was slowing. Instead, they found the opposite. The expansion was accelerating. Distant galaxies were receding faster than nearby ones, and the rate of recession was increasing over time. This was shocking. It was like throwing a ball into the air and watching it speed up instead of slowing down. Something was pushing space apart, counteracting gravity, driving the acceleration. We call it dark energy. Dark energy makes up roughly 68% of the universe. It's the dominant component of everything that exists. More than dark matter, far more than normal matter. And yet, we understand it even less than we understand dark matter. The leading hypothesis is that dark energy is a property of space itself. Einstein's equations of general relativity allow for something called the cosmological constant, a term that represents the energy density of empty space. If space has a small positive energy density, it would exert a kind of negative pressure, pushing space apart instead of pulling it together. This sounds strange, but the math works. A cosmological constant with the right value would explain the observed acceleration perfectly. The problem is that we don't know why space would have this energy, or why it would have the particular value it does. When physicists try to calculate the energy density of empty space from first principles, they get an answer that's about 120 orders of magnitude too large, one of the biggest discrepancies in the history of science. We call this the cosmological constant problem, and it remains unsolved. Dark energy is real, we see its effects, but we don't understand its origin. Some physicists have proposed alternative explanations. Perhaps dark energy isn't constant. Perhaps it's a dynamic field that changes over time, sometimes called quintessence. Perhaps our understanding of gravity on cosmic scales is incomplete, and what we're seeing as dark energy is actually a modification of Einstein's equations. Perhaps the universe is more complicated than we thought, with hidden dimensions or exotic physics we haven't discovered. For now, the cosmological constant remains the best fit to the data, but the mystery is far from solved. What does dark energy mean for the future of the universe? The implications are profound, and depending on your perspective, either terrifying or liberating. If dark energy remains constant, the expansion of the universe will continue to accelerate forever. Distant galaxies will recede faster and faster, eventually crossing our cosmic horizon and becoming invisible. The observable universe will shrink, not because it's actually getting smaller, but because light from distant regions will no longer be able to reach us. In the very far future, trillions of years from now, an observer in our galaxy might look up at the night sky and see only local stars. All the other galaxies will have vanished, carried beyond the horizon by the relentless expansion of space. The cosmos will seem smaller, lonelier, and colder. Eventually, the stars themselves will burn out. The galaxies will go dark. Black holes will evaporate through Hawking radiation, and what remains will be a cold, empty void, stretched thin by dark energy, approaching but never quite reaching absolute zero. This is sometimes called the heat death of the universe. It's not a dramatic ending, no explosion, no collapse, no sudden catastrophe, just a slow fading, a gradual dimming, an approach to eternal stillness. But that's an unimaginably long time from now, trillions upon trillions of years. For tonight, the universe is still full. The sky is still bright with galaxies. The expansion continues, but it hasn't yet hidden our cosmic neighbors from view. Dark energy is pushing the universe apart, but it hasn't finished yet. We still have time, more time than we can comprehend, to explore, to wonder, to appreciate the cosmos while it's still visible. And maybe, before the end, we'll understand what dark energy actually is. Maybe we'll solve the cosmological constant problem. Maybe we'll discover new physics that rewrites everything we think we know. Or maybe we won't. Maybe dark energy will remain mysterious, a force we can measure but never explain. Either way, it's there, woven into the fabric of space, stretching the universe toward its final, quiet destiny. Let's drift a little further. Segment 24, the loneliest galaxy. Some galaxies exist in crowded neighborhoods, clusters containing thousands of members, gravitationally bound together, interacting, merging, evolving in concert. Our own Milky Way is part of a small group called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller companions. We're not alone. But other galaxies are not so lucky. Some drift through voids so vast, so empty, that no other galaxy is visible from anywhere within them. These are the loneliest places in the universe. Imagine being a civilization in one of these isolated galaxies. Your astronomers develop telescopes. They scan the sky, looking for other galaxies, the island universes that populate our own cosmic neighborhood. They search and search, using increasingly powerful instruments, probing deeper and deeper into the darkness. And they find nothing. No spiral arms glowing in the distance, no elliptical blobs of ancient stars, no clusters, no groups, no companions of any kind, just their own galaxy, surrounded by hundreds of millions of light years of empty space. For centuries, perhaps millennia, they might believe that their galaxy is the entire universe, that beyond their stars, there is simply nothing. They would have no conception of the cosmic web, of the billions of galaxies that fill the observable universe. They would look up at their night sky and see only their own stars, scattered across a darkness that seems to go on forever. Eventually, with powerful enough instruments, they might detect faint, distant smudges, other galaxies, far beyond their void. But confirming these observations would take generations. The light from those distant galaxies would be so dim, so shifted by the expansion of the universe, that distinguishing them from instrumental noise would be a monumental challenge. And even if they confirmed the existence of other galaxies, reaching them would be impossible. The distances are too vast, the voids too empty. One such lonely galaxy is MCG plus 0102015. Located in a void so empty that no other large galaxy is visible for millions of light years in any direction, it drifts in cosmic solitude. From inside that galaxy, the night sky would be almost entirely dark except for local stars. The Milky Way's familiar band of distant suns, the edge-on view of our own galaxy, would have no counterpart there. Just individual stars, and beyond them, blackness. What would it be like to grow up in such a galaxy? To live your entire life believing that your few 100 billion stars are all there is? Would it be peaceful, or would it be terrifying? Would the absence of cosmic neighbors feel like freedom or like imprisonment? There's something melancholy about isolated galaxies. They contain everything a galaxy should contain: stars, planets, perhaps even life. But they're cut off from the cosmic community. They exist in silence, surrounded by emptiness, unable to share their light with anyone but themselves. And yet, they persist. The stars within them continue to burn. The planets continue to orbit. The processes of cosmic evolution continue, regardless of whether anyone is watching. The lonely galaxies don't need neighbors to exist. They shine for themselves, for their own stars, for whatever life might or might not inhabit them. There's a lesson in that, perhaps, about finding meaning in isolation, about shining even when no one is watching, about existing fully, completely, without needing an audience. Some of the loneliest galaxies in the universe have been doing this for billions of years. They formed in the early cosmos, drifted into voids as the cosmic web took shape, and have been burning in solitude ever since. They've outlasted empires that never rose, civilizations that never evolved, planets that never formed elsewhere in their cosmic neighborhood. And they'll probably continue long after our own galaxy has merged with Andromeda, long after the local group has collapsed into a single super-galaxy, long after the cosmic horizon has shrunk and isolated every structure from every other. In the end, maybe every galaxy will be lonely. Dark energy will push the universe apart, and the cosmic community will dissolve into isolated islands. What seems exceptional now, the profound solitude of MCG +01, 02, 01 fame, may become the norm. But that's a very long time from now. Tonight, we still have neighbors. We can still see Andromeda with the naked eye, a faint smudge in the northern sky, the light from 1 trillion stars that left their homes 2.5 million years ago. We're part of something larger, connected to a cosmic web that spans billions of light years. Let's appreciate that while we can. Segment 25. The edge of the observable universe. The farthest light. There's a boundary to what we can see, not because the universe ends, we don't think it does, but because light travels at a finite speed, and the universe has existed for a finite time. Light from beyond a certain distance simply hasn't had time to reach us yet. This boundary is the edge of the observable universe, and it surrounds us in every direction like the surface of an immense invisible sphere. The edge is roughly 46 billion light years away. This might seem strange if the universe is only 13.8 billion years old. How can we see things 46 billion light years away? The answer is expansion. While the light was traveling toward us, space itself was stretching. The photons that are just now reaching our telescopes left their sources when the universe was much smaller, much denser, much younger. They've been traveling ever since, and in that time, the universe has expanded enormously. The sources that emitted those photons are now much farther away than they were when the light began its journey. So the observable universe has a radius of about 46 billion light years, giving it a diameter of roughly 93 billion light years. Within this sphere, we estimate there are about 200 billion galaxies. Each galaxy contains billions of stars. Each star might have planets. The numbers are so large that they become abstract, meaningless strings of digits that our brains can't actually process. And this is just what we can observe. The total universe might be infinitely larger. It might contain more galaxies than there are atoms in the observable universe. It might go on forever, in every direction, repeating patterns we'll never see, hosting structures we'll never imagine. Or it might have some finite size and shape we haven't discovered yet. Perhaps it's curved, like the surface of a higher dimensional sphere. Perhaps it wraps around on itself, so that if you traveled far enough in one direction, you'd eventually return to where you started. We don't know. We might never know. What we do know is that the edge is receding. The expansion of the universe is carrying the cosmic horizon outward. Every year, more of the universe becomes visible to us, at least in principle. Photons that had never reached Earth before are arriving for the first time, carrying information from regions we'd never seen. But at the same time, dark energy is accelerating the expansion, and this creates a paradox. While new regions are technically becoming visible, other regions, ones we can see now, are being carried beyond our reach. The expansion is happening faster than light can travel, in a sense. Not that anything is moving faster than light. That's impossible. But space itself is stretching faster than light can cross it. In the far future, this will have profound consequences. Distant galaxies will be carried beyond the cosmic horizon. Their light will stretch into longer and longer wavelengths, becoming radio waves, then microwaves, then fading into invisibility. One by one, galaxies will wink out of existence, not because they've disappeared, but because their light can no longer reach us. Trillions of years from now, an observer in our galaxy, or whatever our galaxy has become by then, might look up at the sky and see only local stars. All the distant galaxies will have vanished. The cosmic microwave background will have faded below detectability. The evidence that the universe was ever larger, more populated, more connected, all of it will be gone. To that future observer, the universe might seem small and finite, a single galaxy surrounded by infinite darkness. They might have no idea that billions of galaxies once filled the sky. They might develop cosmological theories that are completely wrong based on the limited evidence available to them. It's a sobering thought. We happen to live at a time when the cosmic story is still visible. We can see the evidence of the Big Bang. We can observe distant galaxies. We can map the cosmic web. But this window won't be open forever. The universe is slowly drawing its curtains, hiding its history, erasing its past. Some have called this the cosmic dark ages, not the original dark ages after the Big Bang, but a future era when the observable universe has shrunk to almost nothing. It's the ultimate ending, not a bang, but a fade, not destruction, but isolation. But we don't need to worry about that tonight. The curtains are still open. The cosmos is still visible. The light from billions of galaxies is still reaching us, carrying messages from across space and time. Take a moment to appreciate that. Right now, photons that left their sources billions of years ago are landing on Earth. Some of them were emitted before our planet existed. Some of them were emitted before our sun ignited. Some of them have been traveling since the first galaxies formed, crossing billions of light years of expanding space to arrive here, tonight, and be absorbed by our telescopes. Each photon is a message, a time capsule, a whisper from the ancient universe, telling us what things were like long before we existed. And somewhere beyond the edge, beyond the farthest light we can see, there's more. More galaxies, more stars, more planets, more stories we'll never know. The observable universe is just a small bubble in something much, much larger. We'll never see what's beyond. We'll never know what's out there. But we can imagine it. We can wonder about it. We can lie here in the quiet darkness and feel the vast unknown pressing gently against the edges of our tiny, illuminated sphere. That's not frightening. That's wonderful. Let's drift toward rest now.